12,000 years ago, somewhere beneath a sky untouched by electric light. A small group of humans watched the darkness above them change. You can imagine yourself sitting among them near a fading fire. The air carries the dry smell of smoke, damp soil, and animal hide. Wood settles softly inside the embers. Beyond the circle of warmth, insects pulse through the grass, while something unseen moves among distant trees. Above you, thousands of stars fill the night. There are far more than most people see today. The Milky Way stretches overhead as a pale river of light, bright enough to command attention. No city glows beyond the horizon. No aircraft crosses the darkness. No satellite drifts silently between the constellations. You have no telescope. You have no written calendar. You do not even have a word for galaxy. Yet the sky is already teaching you. Night after night, certain patterns return. Some stars rise in familiar places, while others disappear with the seasons. The moon changes shape in a slow and dependable rhythm. The sun moves along the horizon as months pass. These patterns matter because your survival is tied to them. A changing sky can accompany migrating animals, seasonal rains, colder nights, or the ripening of useful plants. Knowing when these changes approach can mean finding food rather than arriving after everything has moved elsewhere. The heavens are therefore not decoration. They are information. You feel the evening cool against your skin, while the last heat leaves the ground. Someone beside you points toward a familiar arrangement of stars. Perhaps the gesture carries a story attached to those lights. We cannot know exactly what was said. Prehistoric people left no written explanation of what they believed about the cosmos. Archaeologists instead work with burials, monuments, artifacts, rock art, and surviving traditions whose connections to deep prehistory remain uncertain. Researchers still debate how deliberately some prehistoric structures were aligned with celestial events. A convincing alignment may represent careful astronomy, religious symbolism, practical seasonal knowledge, coincidence, or several purposes combined. That uncertainty is important. The first astronomy was probably not a single invention. It emerged gradually whenever observant people noticed that the sky repeated itself. You begin with the easiest object to follow. The moon is impossible to ignore. Its pale surface brightens the landscape, disappears, returns as a thin curve, and slowly becomes full again, without artificial lighting. These changes affect how easily you can travel after sunset. A bright moon transforms the night. Paths become visible. Familiar trees gain long shadows. Water catches silver reflections, while distant hills separate themselves from the darkness. Then the moon begins shrinking again. Long before anyone understands orbital mechanics, people can recognize this cycle. Marks carved into bones and stones have sometimes been interpreted as early lunar records, although scholars disagree about many examples. That disagreement gives these objects their quiet mystery. A row of ancient notches might record lunar phases. It might count animals, days, possessions, or something completely different. The maker cannot explain it to you. Only the marks remain. The sun provides another rhythm, slower and more important. If you remain in one place long enough, you notice that sunrise does not occur at precisely the same point every morning. Across the year, its position creeps along the horizon before eventually reversing direction. You do not need mathematics to notice this. You need patience. A particular rock, tree, ridge, or distant mountain can become a natural marker. When the sun rises beside it again, a familiar season may be returning. Generations of observation can transform landscape into calendar. Thousands of years later, communities would construct monuments whose relationships with the sun still fascinate archaeologists. Stonehenge in southern Britain is perhaps the most famous example. Its major axis relates closely to the solstitial sun, but even here, interpretation requires caution. Stonehenge changed across many centuries and served communities whose beliefs cannot be reconstructed completely from stones alone. The sky was useful, but usefulness was never its only power. Imagine watching a total lunar eclipse without knowing its physical cause. The familiar full moon slowly darkens. A curved shadow advances across its face until the moon becomes dim and reddish. The night suddenly feels different. People around you become quieter. Dogs may bark. Children may wake. The air itself seems strangely attentive, although nothing in the atmosphere has actually changed. Then the moon returns. Solar eclipses are even more unsettling. Daylight weakens unexpectedly. Shadows sharpen. Temperatures can fall. Birds may change their behavior as the sun becomes a dark disk surrounded by an unfamiliar brightness. For someone without predictive astronomy, such an event can feel profoundly unnatural. Yet repeated observation eventually reveals that even frightening skies possess patterns. That realization is revolutionary in its own quiet way. The heavens are not completely random. Certain events return. Certain lights wander. Most stars preserve their relationships with neighboring stars, but a handful behave differently. They move slowly against the stellar background over successive nights. Much later, these wandering lights will be understood as planets. For now, they are peculiar travelers. Venus can become exceptionally brilliant near sunrise or sunset. Mars sometimes appears noticeably reddish. Jupiter can dominate a dark sky with a steady brightness. You watch them without knowing that they are worlds. That thought is worth lingering over. For almost all human history, nobody standing beneath the sky knew that Mars possessed volcanoes, that Jupiter had enormous storms, or that Saturn carried rings of ice. The information was always arriving as light. Human eyes simply lacked the instruments needed to extract it. Still, ancient observers learned remarkable things using nothing more complicated than memory, landmarks, careful attention, and communication between generations. Stars could help travelers preserve direction. The sky could announce seasons. Moonlight could influence when journeys were convenient. Celestial cycles could become woven into ceremonies, stories, agriculture, and ideas about death or ancestry. There is also a charming practical problem hidden inside early astronomy. The heavens refuse to keep conveniently matching schedules. A lunar cycle does not divide neatly into the solar year. Anyone trying to coordinate months with seasons eventually discovers that nature has provided several clocks which stubbornly decline to agree perfectly. Human beings have been correcting calendars ever since. For now, however, there are no formal observatories around you. There is only the horizon. You sit near the fire as its orange glow weakens. Smoke rises, bends with the breeze, and disappears into darkness. Your eyes adjust further. More stars emerge. Somewhere overhead lies the light of stars, hundreds or thousands of light years away. Their photons began traveling toward Earth long before tonight, although nobody around your fire could possibly imagine such distances. Far beyond those stars are galaxies invisible to your eyes. Beyond them stretches an observable cosmos whose dimensions would have sounded meaningless even to much later civilizations. And behind everything you see lies an even deeper history. The hydrogen inside many stars was forged during the universe's earliest minutes. Heavier elements in the ground beneath you were produced through generations of stellar evolution. The calcium in your bones has a cosmic ancestry. The iron carried in human blood belongs to that same immense story. But you do not know this yet. That is precisely where our journey must remain for now. You know only what the sky allows an unaided human observer to discover. You know repetition. You know brightness and darkness. You know that the moon changes, the seasons return, and several mysterious lights wander among apparently fixed stars. For thousands of generations, these observations accumulate. Stories preserve some of them. Rituals may preserve others. Practical knowledge passes quietly between parents, children, travelers, farmers, hunters, and communities separated by enormous distances. Eventually, villages become cities. Harvests become organized on larger scales. Writing appears in several regions. Administrators begin recording quantities, payments, floods, and dates. And once human beings learn to preserve information beyond a single lifetime, the sky can be recorded differently too. A person no longer needs to remember every observation. Clay can remember. Stone can remember. Writing can remember. The universe has been shining above Earth for billions of years, indifferent to whether anyone understands it. But now, one small species has begun doing something unusual. It is keeping notes, and those notes will slowly transform wonder into astronomy. Thousands of years later, another kind of observer looks upward. You are no longer sitting beside a small prehistoric fire. Around you stand mud-brick houses, workshops, temples, crowded streets, and fields maintained by communities whose lives depend upon organized agriculture. Civilization has changed the relationship between humanity and the sky. The stars remain exactly as mysterious. Humans have become better at remembering them. In ancient Mesopotamia, between the Tigris and Euphrates rivers, generations of observers begin recording celestial events with extraordinary persistence. You can imagine climbing above the sleeping streets on a clear evening. The day's heat still lingers inside the walls. You smell dust, smoke, oil lamps, animals, and damp earth carried from irrigated fields. Voices fade below while the open sky becomes darker. A clay tablet rests nearby. Now an observation can survive its observer. That simple development changes astronomy profoundly. Writing allows one generation to compare its sky with observations made decades or centuries earlier. Patterns too slow for one lifetime can gradually become visible. Babylonian astronomy becomes particularly sophisticated. Observers record appearances of planets, lunar behavior, eclipses, and other celestial phenomena. Their surviving astronomical texts demonstrate careful numerical methods and systematic attention extending across long periods. This is not astronomy as modern scientists practice it, but it is no longer casual sky watching either. You are witnessing measurement becoming tradition. The moon remains especially useful because its changing phases provide an obvious way to divide time. Months can be organized around lunar cycles, although those cycles still refuse to cooperate neatly with the solar year. The old calendar problem remains. 12 lunar months are shorter than a solar year, so a purely lunar calendar gradually slips away from the seasons. Ancient administrators, therefore, need methods for keeping agricultural and ceremonial dates appropriately aligned. Occasionally, an additional month can help. It is an elegant solution to an inconvenient universe. The Babylonians also become remarkably skilled at recognizing cycles associated with eclipses. They cannot explain eclipses using modern gravitational physics, but prediction does not require complete understanding. This distinction will appear repeatedly throughout astronomical history. You can know that something happens before knowing why. Imagine the practical authority created by such knowledge. An eclipse that terrifies an unprepared population becomes less mysterious when specialists have reason to expect it. Celestial events can therefore become entangled with government, religion, omens, and political power. Babylonian scholars sometimes interpreted unusual heavenly events as signs affecting kings or kingdoms. To modern ears, astronomy and divination seem like different activities. For them, the boundary was not so simple. The same person might carefully record a planetary position while also asking what that position meant for events on Earth. Accurate observation and supernatural interpretation could coexist without seeming contradictory. One quirky example involves substitute kings. In some Mesopotamian traditions, an ominous celestial prediction could lead authorities to temporarily install a substitute ruler while the real king remained protected from the predicted danger. The heavens apparently generated administrative complications, yet beneath such practices was an increasingly impressive body of observational knowledge. Farther southwest, another civilization develops its own intimate relationship with the sky. You travel in imagination toward ancient Egypt. The atmosphere changes. Dry air settles over the Nile Valley, and the smell of river mud mingles with reeds, animals, cooking fires, and sun-warmed stone. Beyond the cultivated land waits an enormous desert. At night, darkness becomes magnificent. Egyptian life depends heavily upon seasonal rhythms, especially those connected with the Nile. Astronomy, timekeeping, religion, agriculture, and royal authority become woven together in ways difficult to separate neatly. Certain stars acquire particular importance. The bright star Sirius became associated with seasonal and calendrical patterns connected with the Nile region. Its annual reappearance in the morning sky held considerable significance within Egyptian timekeeping and culture, but ancient practices changed over centuries. Scholars continue discussing precisely how particular astronomical observations related to calendars, temple orientations, religious ideas, and administrative systems during different Egyptian periods. The evidence rarely gives one simple answer. What remains clear is that Egyptians watched the sky carefully. They divided portions of the night using groups of stars whose appearances helped mark passing hours. These stellar timekeepers are commonly called deacons. Imagine trying to tell time without a clock. You wait beneath the stars and watch particular patterns rise or cross expected positions. The sky itself becomes the face of an enormous celestial timepiece. It requires clear weather. Fortunately, Egypt can be accommodating. The sun also provides a more immediate clock during daylight. Shadow clocks and related methods allow changing solar shadows to divide portions of the day. Time is becoming something people can organize more precisely. Across other regions, similar developments occur independently. Communities observe solstices and equinoxes. Farmers connect celestial appearances with seasonal tasks. Sailors learn relationships between stars and direction. Different cultures divide the sky differently. That matters. The constellations familiar to many people today are not universal pictures naturally drawn between stars. They are cultural interpretations imposed upon scattered points of light. One community sees an animal, another sees a hero, another may see tools, ancestors, spirits, or entirely different patterns. The stars do not connect themselves. Humans connect them. You can feel how important storytelling remains even as measurement improves. A memorable celestial story can preserve relationships between stars more easily than an abstract list of positions. Story and observation can reinforce each other. Meanwhile, the physical universe above these civilizations continues following processes nobody yet suspects. Earth rotates once each day, creating the apparent movement of the heavens. Earth travels around the sun, producing annual changes in which stars dominate the night. The moon orbits Earth. The planets orbit the sun. But if you stand on Earth without instruments or modern theory, almost none of this feels obvious. You feel stationary. The ground beneath your feet appears perfectly stable. The sun rises on one horizon, crosses overhead, and disappears beyond another. Stars perform the same nightly procession. Everything seems to move around you. An Earth-centered universe is therefore not a foolish assumption. It is the natural first impression. If Earth were moving rapidly, you might reasonably ask why you cannot feel the motion. Why does a stone dropped from your hand fall directly downward instead of being left behind? Why do the stars not visibly shift as Earth changes position? These questions will trouble thinkers for centuries. Ancient observers lacked the instruments needed to detect many subtle effects that would eventually provide answers. Still, their measurements grow increasingly precise. Babylonian numerical astronomy will later influence Greek thinkers. Egyptian traditions will interact with Mediterranean scholarship. Knowledge moves through trade, conquest, translation, migration, and simple human curiosity. Ideas travel almost as persistently as people. You can picture a merchant crossing a busy market without realizing that astronomical knowledge is crossing cultural boundaries around him. A tablet is copied. A calendar method is adapted. A traveler describes an unfamiliar constellation. A scholar encounters observations recorded by someone who died generations earlier. Slowly, the sky becomes a shared intellectual problem. The great change is not that ancient civilizations suddenly understand the universe. They do not. They still possess many cosmological ideas shaped by religion, mythology, philosophy, and local tradition. Earth remains the immediate center of human experience. But something crucial has happened. Observation has acquired memory. Once observations can be preserved, predictions can be tested against future events, errors can be noticed, cycles can be refined, the universe begins leaving a written trail through human history. Tonight, you can imagine standing again above a Mesopotamian city. The clay beneath your fingers feels cool now. Below you, lamps flicker between buildings while the river moves quietly through darkness. Somewhere nearby, a stylus presses another set of marks into wet clay. Overhead, Mars drifts among the stars. Nobody yet knows it is a world. Nobody knows that mountains rise from its surface or that ancient water once altered its landscape. But its position is being recorded. For the first time, humanity is building archives large enough for the heavens to reveal patterns across generations. Soon, another question will emerge. Recording where the lights move is useful. But what if you could explain their movements with shapes, numbers, and geometry? By the 6th century BC, the night sky has already been watched for thousands of years. Now, around the Mediterranean, a different habit of thought begins gathering strength. You still look upward at the same moon, planets, and stars. But another question increasingly accompanies the observation. What physical arrangement could produce what you see? You imagine yourself walking through an ancient Greek coastal town after sunset. Warm stone beneath your sandals slowly releases the heat of afternoon. You smell salt from the harbor. Oil lamps flicker inside nearby houses, while ropes knock gently against wooden masts somewhere beyond the waterfront. Voices drift from a gathering where people argue about nature. The Greeks did not invent astronomy. Babylonian observers had already developed sophisticated methods, while Egyptians possessed long traditions of celestial timekeeping. Greek thinkers inherited ideas and observations through a wider world of trade and cultural exchange. What develops here is another approach to the heavens. Geometry becomes increasingly important. If celestial movements follow regular patterns, perhaps circles, angles, distances, and carefully constructed models can explain them. The idea sounds almost modest. Its consequences are enormous. Early Greek thinkers propose many competing pictures of the cosmos. Their surviving writings are incomplete, and later authors sometimes describe ideas centuries after the original thinkers died. Historians therefore continue debating exactly what certain early philosophers believed. That uncertainty follows you into the ancient world. You hear echoes rather than complete conversations. One influential idea eventually places a spherical Earth near the center of a spherical cosmos. The spherical Earth itself is important. Contrary to a popular modern myth, educated people in classical antiquity could possess strong reasons for believing Earth was round. The evidence was available to careful observers. During a lunar eclipse, Earth's shadow falling across the moon appears curved, Travelers moving north or south notice that familiar stars change their height above the horizon. Ships provide another clue. As a vessel disappears into the distance, its lower portions vanish before the highest parts. The effect is consistent with movement across a curved surface. You do not need a spacecraft to suspect a sphere. You need observation. By the 4th century BC, Aristotle presents arguments for a spherical Earth while constructing a broader physical system centered upon it. Stand beneath his imagined universe for a moment. Earth rests near the center. Around it are celestial regions carrying the moon, sun, planets, and stars. The heavens are associated with orderly circular motion, while earthly matter behaves according to different principles. To you, equipped with modern knowledge, the system contains obvious mistakes. To an ancient observer, it explains a great deal. Earth feels motionless. Objects fall toward the ground. The heavens appear to rotate around you every day. Perfect circles also carry philosophical appeal because they possess no obvious beginning or end. There is another problem. If Earth moves around the Sun, nearby stars should appear to shift slightly against more distant stars as your viewpoint changes during the year. This effect is stellar parallax. Ancient observers could not detect it. The stars are simply too distant for naked human eyes to measure the tiny displacement. The absence of visible parallax therefore seemed like evidence against a moving Earth. Unless the stars were unimaginably distant, and unimaginably distant was quite a demand. Still, not everyone accepts the same cosmic arrangement. In the 3rd century BC, Aristarchus of Samos proposes something startling. Earth moves around the Sun. Earth also rotates. You can almost feel the intellectual floor tilt beneath your feet. The idea does not become dominant. We know about it mainly through later references, and much of Aristarchus's original reasoning has been lost. Scholars still discuss how fully his system resembled later heliocentric models, yet the proposal existed. More than 17 centuries before Copernicus, someone had placed Earth in motion around the Sun. Why did the idea fail to conquer astronomy? Evidence mattered. A moving Earth created physical questions ancient science could not easily answer. No stellar parallax could be observed, and Aristotelian physics provided a coherent explanation for an apparently stationary world. Heliocentrism also did not automatically produce dramatically better predictions with the available observations. A clever idea needs more than cleverness. It needs evidence strong enough to defeat its competitors. Meanwhile, astronomers become increasingly capable of measuring the sky. One of the most remarkable is Hipparchus, working during the 2nd century BC. You picture him under a clear Mediterranean night, carefully measuring celestial positions without a telescope. The instruments are mechanical and geometrical. The eyes remain human, yet precision is improving. Hipparchus is associated with an influential star catalogue and important work on the positions and brightness of stars. He also develops sophisticated mathematical approaches to the motions of the sun and moon. Then he notices something extraordinary. Earlier observations do not align perfectly with his own. The celestial coordinate system itself appears to be shifting slowly. Today, you know the reason. Earth's rotational axis gradually changes direction, somewhat like the slow wobble of a spinning top. This motion is called axial precession and unfolds across roughly 26,000 years. Hipparchus could not know its modern physical explanation, but he could detect its effects. That is a beautiful moment in astronomy. A human lifetime is brief, yet preserved measurements allow you to discover a cycle lasting thousands of years. Written memory has extended the reach of observation. There is also a wonderfully human problem buried inside ancient star catalogues. How bright is a star? Without electronic detectors, you judge with your eyes. Hipparchus is traditionally associated with a system that grouped stars according to apparent brightness, an ancestor of the magnitude scale astronomers still use in modified form. The brightest stars received smaller numerical magnitudes. Fainter stars received larger ones. Astronomy has retained this slightly backwards arrangement ever since. Ancient habits can be remarkably durable. Geometry also helps thinkers estimate celestial sizes and distances. Aristarchus attempts to compare the distances of the Sun and Moon by studying their geometry when the Moon appears half illuminated. His numerical result is far from the modern value because the required angle is extremely difficult to measure accurately. But his reasoning points somewhere important. The Sun must be much farther away than the Moon. It may also be much larger than Earth. You begin to sense the universe expanding intellectually, even though its true scale remains hidden. Another famous calculation turns attention toward Earth itself. Eratosthenes, working in the 3rd century BC, estimates Earth's circumference using shadows measured at different locations. The underlying idea is wonderfully simple. If sunlight arrives at slightly different angles in two cities, the difference can reveal the curvature of Earth. A shadow becomes a planetary measuring instrument. You feel the sunlight on your arm. You watch a vertical object cast a narrow line across the ground. Nothing about the scene looks cosmic, yet geometry can connect that little shadow with the size of an entire world. This is the new power developing within ancient astronomy. The heavens can be reasoned about indirectly. You do not need to touch the sun. You measure angles. You compare observations. You build a model and ask whether the sky behaves as that model predicts. Still, major mysteries remain. The planets are particularly troublesome. Most of the time, they drift eastward against the distant stars. Occasionally, however, a planet slows, stops, and appears to move backward before resuming its usual direction. Mars makes this especially noticeable. Retrograde motion demands explanation. If heavenly motion is supposed to be orderly and circular, why does a planet seem to reverse itself? Greek mathematical astronomers developed combinations of circular motions to reproduce these strange paths. Circles begin riding upon circles. The machinery becomes intricate, but complexity alone does not make a model foolish. If a mathematical system predicts what observers see, complexity can be tolerated. That principle will help shape astronomy for many centuries. You return to the harbor as the night deepens. The stones are cooler now. The smell of smoke hangs lightly above the roofs, and waves continue brushing against the dark shoreline. Above you, Mars shines with its quiet reddish light. It looks exactly as it did to prehistoric observers. Humanity has changed. The wandering light now has recorded positions, geometric models, philosophical explanations, and competing interpretations. Earth has become a sphere. Its size can be estimated. The heavens can be mapped. Someone has even dared to set Earth moving around the sun. But the decisive evidence is still missing. For the moment, the cosmos will remain centered upon a stationary Earth. And soon, one astronomer will assemble centuries of observation and geometry into a system so effective that it will shape humanity's picture of the heavens for more than 1,000 years. By the 2nd century AD, Alexandria remains one of the great intellectual crossroads of the Mediterranean world. You enter a city filled with merchants, sailors, officials, craftsmen, teachers, and scholars speaking beneath a hot Egyptian sky. Ships crowd the harbor, bringing goods and ideas from distant shores. The air smells of salt, fish, smoke, spices, and sun-warmed stone. At night, the noise gradually softens. You look upward and find the same old problem waiting patiently among the stars. The planets refuse to move simply. Mars is especially troublesome. Night after night, it usually creeps in one direction against the stellar background. Then its motion slows and appears to reverse. Eventually, it turns again. To an observer standing on Earth, this strange backward loop is real as an appearance. Any successful astronomical system must account for it. Into this long tradition comes Claudius Ptolemy. Little is known with certainty about much of his personal life. He worked in Alexandria, during the 2nd century and inherited astronomical knowledge developed across many earlier generations. His achievement is not simply declaring Earth the center. That idea is already ancient. Instead, Ptolemy organizes mathematical astronomy into an extraordinarily powerful predictive framework. You imagine a scholar working by lamplight. Papyrus rustles beneath his fingers. Oil smoke hangs faintly in the room, and calculations accumulate while the city settles outside. Above him, the planets continue their wandering. Ptolemy's great astronomical work, later widely known as the Almagest, presents mathematical methods for predicting celestial positions. Earth sits motionless near the center of the model, but the planets do not merely travel around Earth on simple circles. The geometry is more elaborate. A planet can move around a small circle called an epicycle. The center of that smaller circle moves along another larger circular path. With carefully selected parameters, these combinations reproduce complicated planetary movements, including retrograde motion. There are additional refinements. Ptolemy uses devices, including eccentric circles, and the equant to improve agreement between mathematical predictions and observations. To modern listeners, this may sound unnecessarily complicated, but remember what you can actually see. You stand on a world that feels stationary. You watch the entire sky appear to rotate around you. You cannot detect Earth's orbital motion through naked eye stellar parallax. The geocentric model fits ordinary experience remarkably well. More importantly, it calculates. That matters enormously. A mathematical model does not survive for centuries merely because people are stubborn. It survives because, within the precision available, it continues doing useful work. Ptolemy's system could predict planetary positions with considerable success. It connected geometry with observation. It offered astronomers a practical framework that could be studied, corrected, and applied. There is also an important subtlety. A mathematical device does not always tell you what an astronomer believes physically exists. Historians still discuss how ancient astronomers understood the relationship between geometrical models and the actual machinery of the heavens. Were every circle and mathematical point physically real, or were some primarily computational tools? Different thinkers could answer differently. The distinction between a model and reality will haunt science long after Ptolemy. Even modern cosmology faces versions of that question. For now, you remain beneath the Alexandrian sky. The moon crosses steadily westward as Earth rotates beneath it. Although nobody around you describes the nightly motion that way, Ptolemy also preserves a large catalogue of stars. He organizes constellations and provides coordinates for more than 1,000 stellar entries. Some information draws upon earlier traditions, particularly work associated with Hipparchus. Determining precisely which observations originated with whom remains a subject of scholarly investigation. The stars themselves offer few explanations. They simply shine. One curious feature of Ptolemaic astronomy is how much mathematical ingenuity can emerge from an incorrect physical arrangement. The central assumption is wrong. Earth is not stationary at the center of the planetary system. Yet much of the mathematics can still approximate what observers see. This is not unusual in science. A model may capture patterns effectively while misunderstanding deeper causes. You can predict a shadow without understanding nuclear fusion inside the sun. You can recognize tides without possessing Newtonian gravity. Knowledge often arrives in layers. Ptolemy's universe also feels satisfyingly ordered. Earth occupies the central region, while celestial motions unfold around it according to mathematical rules. Beyond the planets lies the realm of stars. The true universe is almost unimaginably larger. The nearest star beyond the Sun is more than 4 light-years away. The Milky Way contains hundreds of billions of stars, and countless galaxies populate the observable cosmos. None of this is accessible to Ptolemy. When he looks at the Milky Way, he sees a luminous band. Individual stars, hidden within much of that glow, remain unresolved by the naked eye. When he looks toward the Andromeda region, He cannot know that light from another enormous galaxy has crossed roughly 2.5 million years before reaching Earth. The universe is already revealing itself. Human senses simply receive too little information. Still, Ptolemy does something essential. He makes celestial predictions systematic. Imagine following a planet across months. You record its longitude against the stellar background. You compare the observation with a calculated position. A difference appears. Perhaps the observation is imperfect. Perhaps the parameters need refinement. Perhaps the model itself contains a deeper problem. That habit of comparison becomes increasingly important. Models can be confronted with the sky. There is gentle irony here. The Ptolemaic system will eventually help create conditions for its own replacement by preserving mathematical astronomy and encouraging precise prediction. It provides later astronomers with a framework they can test. Every successful prediction strengthens confidence. Every persistent discrepancy invites adjustment. Centuries will pass. Empires will rise and fragment. Languages of scholarship will change. Manuscripts will be copied, translated, commented upon, and carried across political boundaries. Ptolemy's astronomy will travel with them. The knowledge does not move in a straight line. Some texts disappear from particular regions while surviving elsewhere. Scholars inherit incomplete traditions, restore them, criticize them, and combine them with new observations. Astronomy becomes a relay across civilizations. That is easy to forget when history is reduced to famous names. No scientist works alone with the universe. Behind every celebrated observer stand instrument makers, translators, copyists, teachers, patrons, calculators, anonymous assistants, and earlier generations whose measurements made later discoveries possible. Even the simplest star table contains accumulated human labor. Outside Alexandria, ordinary people continue using the sky in more immediate ways. Sailors watch stars while navigating. Farmers notice seasonal appearances. Travelers orient themselves beneath familiar constellations. Religious calendars follow celestial cycles. Most people never calculate an epicycle. They do not need to. For them, the heavens remain simultaneously practical, beautiful, and mysterious. You can imagine leaving the city walls late at night. The smell of the harbor weakens behind you. Sand shifts softly beneath your feet, and the air becomes cooler, away from crowded streets. The stars seem brighter here. Mars hangs above the horizon. According to Ptolemy's mathematics, its future position can be calculated within the limits of the system. That is an extraordinary achievement. Humanity has moved from noticing that a wandering light returns to constructing geometry capable of predicting where it will wander next. Yet the deeper truth remains concealed. Mars appears to loop backward, because Earth and Mars are both moving around the Sun at different speeds. No epicycle is required in the modern explanation. But humanity cannot simply leap to that answer. It must earn it through better measurements, new physical ideas, and instruments that do not yet exist. For centuries, Ptolemy's cosmos will remain useful. Then political and intellectual centers will shift. Far from Alexandria, scholars working across the medieval Islamic world will receive this inherited astronomy and refuse merely to store it. They will calculate, they will measure, they will criticize, and beneath new observatory skies, tiny imperfections in the ancient machinery will become increasingly difficult to ignore. By the 9th century, the centers of astronomical scholarship have shifted across a changing world. You find yourself beneath the evening sky of Baghdad, where streets gradually cool after another hot day. Lamps glow behind walls, while merchants finish their business and families retreat indoors. The smell of bread, dust, smoke, and animals lingers in the air. Above everything, the stars remain familiar. The planets still wander through the constellations, just as they did over Babylon, Egypt, Greece, and Alexandria. Yet the people studying them now inherit centuries of mathematical astronomy. Knowledge has crossed borders again. Greek scientific works are translated, studied, discussed, and compared with traditions from other regions. Astronomers encounter Ptolemy not as an untouchable authority, but as a remarkably capable predecessor whose results can be examined. That difference matters. Preserving knowledge is only part of the story. Medieval Islamic astronomers test it. They calculate planetary positions, improve astronomical tables, refine mathematical techniques, and build instruments capable of increasingly careful measurement. You can imagine entering a scholarly room after sunset. Paper lies across low tables. Metal instruments catch the yellow light of oil lamps, and quiet conversation mixes with the faint scratching of pens. Someone is calculating where a planet should appear. Someone else intends to look. Astronomy is becoming increasingly collaborative and institutional. One important development occurs during the 9th century, when astronomers associated with the Abbasid court conduct observations intended to refine inherited astronomical parameters. Measurements of Earth's size are also attempted. The idea itself is not new. Eratosthenes had estimated Earth's circumference many centuries earlier. What is striking is the continuing desire to measure the world again, rather than simply accept an ancient number. The Earth beneath your feet can be tested. So can the sky above you. Among the influential astronomers of this broad intellectual world is Al-Battani, whose observations around the 9th and 10th centuries improve measurements connected with the solar year and celestial motions. His work later reaches European astronomers through translation. The relay continues. Another major figure is Ibn al-Haytham, known especially for his work on optics. Understanding light eventually becomes essential to understanding the universe, because almost everything astronomers know arrives through some form of radiation. For now, optics concerns questions much closer to human experience. How does vision work? How does light travel? What happens when it reflects or passes through transparent materials? These questions may seem separate from planetary astronomy. They are not. Centuries later, telescopes will depend upon precisely controlled light. Spectroscopes will divide starlight into wavelengths. Cameras will collect photons too faint for human eyes. The road toward modern cosmology passes quietly through the study of vision. You step outside again. Night air touches your face, and the city sounds become softer. Somewhere, water moves through a channel while a dog barks beyond the walls. A bright planet hangs above the rooftops. An astronomer may use an astrolabe to determine celestial positions or time. The astrolabe is among history's most elegant scientific instruments. Its metal plates and rotating components can represent aspects of the sky in a portable, mathematical form. Hold one in your hand, and you are carrying a small mechanical interpretation of the heavens. It can assist with timekeeping, astronomical calculation, surveying, and other practical tasks depending upon its design. It is also beautiful. Scientific instruments frequently are. Their makers combine mathematical understanding with metalworking skill, producing objects where craftsmanship and abstract knowledge become inseparable. Astronomy depends upon such people. A brilliant theory is not enough if nobody can build the instrument needed to test it. As centuries pass, observatories become increasingly ambitious. In the 13th century, the Maraga Observatory in present-day Iran becomes an important center of astronomical research. Here, astronomers examine problems within Ptolemaic planetary theory and develop alternative mathematical devices. One famous construction is associated with Nasir al-Din al-Tusi. The arrangement, now called the Tusi couple, combines circular motions to generate an oscillating straight-line motion. It is clever mathematics. More importantly, it demonstrates dissatisfaction with particular features of inherited planetary models. Ptolemy remains respected, but respect does not prevent criticism. Later astronomers continue the work. In the 15th century, Samarkand becomes home to another extraordinary observatory associated with Ulugh Beg. Imagine approaching the complex beneath the clear Central Asian sky. The air can be cold after sunset. Stone radiates the day's remaining warmth, while enormous astronomical structures allow observers to measure celestial positions with impressive precision. Ulugh Beg and his collaborators produce a major star catalogue. These observations are made without telescopes. That is worth remembering. When you hear observatory today, you may picture a dome containing a giant mirror and electronic detectors. Here, the primary technology is geometry-made architectural. Large instruments increase precision, because larger scales make small angular differences easier to distinguish. Human eyesight remains the final detector. The observatory amplifies what the eye can measure. A quirky reality of pre-telescopic astronomy is that enormous instruments could sometimes outperform smaller portable ones, simply because size made their markings easier to read accurately. Sometimes better science requires a larger ruler. Yet the medieval astronomical world is not unified. Scholars disagree about planetary models, physical explanations, mathematical techniques, and the relationship between astronomy and philosophy. Researchers today also debate how particular developments moved between intellectual traditions. Connections between later European heliocentric astronomy and earlier Islamic mathematical models are especially fascinating. But establishing exact lines of transmission can be difficult. Similar mathematics can reveal influence. It does not always reveal the root. Manuscripts disappear. Teachers leave incomplete records. Ideas can travel without biographies attached. Meanwhile, astronomy is also developing elsewhere. Chinese observers maintain long traditions of recording celestial events, including comets, eclipses, unusual stars, and planetary phenomena. Their records later become valuable to modern astronomers studying events that occurred centuries ago. In 1054, observers in East Asia recorded a brilliant new object in the sky. It remained visible for an extended period. Today, astronomers associate that event with the supernova whose remnant is the Crab Nebula. Think about what actually happened. A massive star reached the end of its life thousands of light years away. Its core collapsed, releasing an enormous burst of energy. The light crossed interstellar space for millennia. Then, during the medieval period on Earth, human eyes received it. People had no concept of a supernova. They could still record the visitor. Nearly 1,000 years later, those written observations help scientists understand the remains of the explosion. The ancient habit of keeping notes continues paying dividends. Across Europe, astronomical learning also persists and gradually expands through monasteries, cathedral schools, courts, and later universities. Translations from Arabic and Greek sources bring substantial bodies of mathematical and philosophical knowledge into Latin scholarship. Ptolemy becomes influential there once again. Aristotle becomes deeply important. Earth remains stationary within the dominant cosmological framework. This is not simply because medieval thinkers refuse alternatives. The observational problems facing a moving Earth remain difficult. No stellar parallax is visible. Everyday physics still seems to favor stability beneath your feet, and Ptolemaic mathematical methods remain useful. A model with centuries of successful application cannot be displaced by elegance alone. You need a better system. You need observations capable of distinguishing between competing arrangements. You need new physics. Eventually, you will need a telescope. None of those pieces has arrived together yet. So you remain, for another moment, beneath the medieval sky. You feel cold metal from an astronomical instrument against your fingertips. Nearby, someone reads a measured angle by lamplight. The smell of oil and paper mixes with the night air. Above you, Saturn moves almost imperceptibly. The astronomer does not know that rings surround it. Jupiter appears as a single bright point because its moons remain invisible to the unaided eye. Venus shines beautifully without revealing its phases, clearly enough to settle the structure of the planetary system. The evidence needed for the next transformation is tantalizingly close. Humanity has preserved ancient astronomy, improved its mathematics, challenged its imperfections, and constructed increasingly precise instruments. The old Earth-centered cosmos has become more sophisticated than ever. That sophistication will soon make its weaknesses easier to see. In Renaissance Europe, a quiet mathematical proposal will place the Sun near the center once again. Then another observer will spend decades measuring the planets with almost obsessive precision. Between them, the ancient universe will begin to move. In 1543, an elderly Polish scholar named Nicholas Copernicus lay near death as his great astronomical work finally appeared in print. You can imagine the heavy volume arriving into a Europe already transformed by printing, navigation, religious upheaval, and expanding intellectual exchange. Outside, carts grind over uneven streets. Inside, paper smells faintly of ink and glue. Pages turn beneath careful fingers, revealing diagrams that rearrange humanity's familiar heavens. Earth is moving. For centuries, educated astronomers had worked successfully with versions of an Earth-centered cosmos. Now, Copernicus places the Sun near the center of the planetary arrangement and makes Earth another moving world. The proposal is not completely unprecedented. Aristarchus had suggested a moving Earth in antiquity. Medieval scholars had also explored questions concerning celestial motion and the mathematical difficulties within Ptolemaic astronomy. Copernicus nevertheless creates something powerful. He organizes heliocentrism into a comprehensive mathematical system. You stand within his imagined cosmos. Earth rotates once each day, so the daily sweep of the heavens no longer requires the entire universe to spin around you. Earth also travels around the Sun. The other known planets do the same. Suddenly, retrograde motion begins to look different. Mars does not truly reverse its orbit. Earth, traveling along an inner and faster orbit, periodically overtakes Mars. From your moving viewpoint, the distant planet temporarily appears to drift backward against the stars. You can reproduce something similar during an ordinary journey. Look from a moving carriage at another traveler farther away. Relative motion can make that person seem to slide backward against the distant landscape. Nothing has actually reversed direction. The observer has moved. This is an elegant explanation, but elegance is not proof. Copernicus still relies heavily upon combinations of circular motion because circles retain their ancient mathematical appeal. His system does not instantly make planetary prediction wonderfully simple. There are still adjustments and geometrical complications. A common story claims that Copernicus swept away messy epicycles and replaced them with clean circles around the Sun. Reality is less tidy. Scientific revolutions usually are. His model also faces an old observational difficulty. If Earth travels around the Sun, why can nobody detect annual stellar parallax? Copernicus can answer that the stars are extraordinarily distant. That answer is correct, but 16th-century astronomers cannot yet demonstrate it. You look toward the stars with your unaided eyes. They appear like tiny points arranged upon a distant surface. Their true distances are so enormous that Earth's entire orbit produces shifts too small for available instruments to measure. The universe must therefore be much larger than many people imagined. Heliocentrism quietly enlarges the cosmos. Not everyone is persuaded. Astronomers have practical reasons to remain cautious. The Ptolemaic tradition has accumulated centuries of mathematical refinement, while Copernicus has not produced decisive new observational evidence for Earth's motion. There are also physical questions. If Earth spins, why are people not thrown from its surface? Why does a stone dropped from a tower land near its base? Why do clouds and birds apparently share Earth's motion? Later physics will answer these questions. Copernicus cannot fully do so. For the moment, the heavens contain competing possibilities. Then a Danish nobleman begins measuring them with astonishing care. Tycho Brahe is born in 1546. His life eventually becomes almost as memorable as his observations. He possesses wealth, ambition, political connections, a famously damaged nose, and an intense commitment to precision. The lost portion of his nose followed a youthful jewel. He later wore a metal replacement. Astronomy has rarely lacked personality, yet the amusing details can distract from Tycho's extraordinary scientific importance. He observes before the invention of the astronomical telescope. His instruments rely on carefully constructed angular scales, sighting devices, quadrants, and other equipment designed to measure celestial positions. You imagine standing at Uraniborg, his observatory on the island of Haven. Wind moves across the island. The night smells of grass, sea air, smoke, and cold metal. Assistants work nearby, while enormous instruments wait beneath the stars. Your fingers become stiff in the evening chill. Tycho demands accuracy. Again and again, planetary positions are measured. Mars receives particular attention. Those measurements will later become priceless. Before that happens, however, the sky delivers something dramatic. In 1572, Tycho observes a brilliant new star in the constellation Cassiopeia. Today, you know it was a supernova. To Tycho, its importance lies partly in where it appears to be. Aristotelian cosmology traditionally describes the distant celestial realm as fundamentally unchanging. A genuinely new object among the stars would be troublesome. Tycho measures the object's position and looks for parallax. He finds no detectable shift, indicating that it is nearby. The new light therefore appears to belong far beyond the moon. Change has occurred in the supposedly unchanging heavens. Then another challenge arrives. In 1577, a bright comet crosses the sky. Comets had often been treated within Aristotelian natural philosophy as atmospheric phenomena. Tycho's measurements again suggest something farther away. The comet appears to pass through regions where traditional solid celestial spheres might have been expected. The old cosmic architecture begins to look less secure. Tycho still does not accept Copernicus's moving Earth. Instead, he develops a hybrid arrangement. Earth remains stationary. The Sun moves around Earth, while the other planets move around the Sun. This Tychonic system preserves a stationary Earth while capturing important geometrical advantages associated with heliocentrism. It is a serious competitor. History can make discarded models seem absurd after the outcome is known. They rarely felt absurd beforehand. Tycho lacked evidence capable of forcing him to accept Earth's motion. His alternative explained many observations while avoiding physical problems associated with a moving world. Scholars still examine the complex mixture of observational, philosophical, mathematical, and religious considerations surrounding these debates. No single motive explains every astronomer's choice. That is how genuine intellectual change usually looks. People disagree for different reasons. Meanwhile, another observer enters the story. Johannes Kepler arrives in Prague and eventually works with Tycho. Their personalities differ sharply. Tycho possesses the observations. Kepler possesses an unusual determination to discover the mathematical architecture hidden within them. The relationship is not always comfortable. That may be putting it gently. Tycho guards his precious planetary data, while Kepler desperately wants access to the measurements needed for his theories. Then in 1601, Tycho dies. Kepler gains greater access to the observational legacy. Now Mars becomes the judge. You can picture sheets of numbers spread across a table. Candlelight trembles over calculations. Wax and smoke scent the room, while Kepler repeatedly tries to fit the planet's observed path to combinations of circular motion. The results almost work. Almost. An error of roughly 8 arc minutes remains between certain predictions and Tycho's observations. 8 arc minutes is a tiny angle. It is roughly 1/4 of the apparent width of the full moon. A less careful observer might dismiss it. Kepler does not. He trusts Tycho's measurements enough to suspect the model instead. That decision is one of astronomy's quiet turning points. A small discrepancy can destroy an ancient assumption when the observations become precise enough. For nearly 2,000 years, circles had dominated ideas about heavenly motion. Now Mars refuses to cooperate. The problem is no longer whether Copernicus had been imaginative enough to move Earth. The deeper problem concerns the shape of planetary paths themselves. Outside Kepler's window, the real Mars continues traveling around the Sun along an ellipse, exactly as it has for billions of years. Humanity simply has not recognized the shape yet. The universe does not adjust itself to philosophical preference. Eventually, the measurements become too accurate for the old perfection to survive. The circle is about to break. In 1609, Johannes Kepler published a conclusion that quietly removed one of astronomy's oldest assumptions. Mars did not travel around the Sun in a perfect circle. Its path was an ellipse. You can imagine Kepler surrounded by papers after years of calculation, with candle smoke drifting through a dim room. Outside, wheels rattle over streets while voices fade into the evening. The numbers have finally yielded. Tycho Brahe's measurements were too precise to ignore, and Mars had refused every attempt to imprison it within perfect circular motion. Kepler accepted what the observations demanded. That sounds straightforward when you already know the answer. For Kepler, it required abandoning an idea with extraordinary intellectual ancestry. Circular celestial motion had survived from ancient philosophy through medieval astronomy and into Copernicus's heliocentric system. Now a tiny discrepancy had broken the circle. An ellipse looks almost disappointingly ordinary. You can draw one with two fixed points, a loop of string and a pencil. Yet this simple shape transforms the architecture of the planetary system. The Sun occupies one focus of a planet's ellipse. It is not positioned neatly at the geometrical center. The planet's distance from the Sun therefore changes throughout its orbit. Kepler discovers something else. The planet does not travel at constant speed. It moves faster when closer to the Sun and more slowly when farther away. You can almost feel the old celestial machinery loosening. The heavens are still orderly. They simply obey a different order. Kepler expresses this behavior through what becomes his second law of planetary motion. A line connecting a planet to the Sun sweeps out equal areas during equal intervals of time. The wording sounds abstract. The meaning is graceful. A planet adjusts its orbital speed according to its position. Years later, Kepler discovers another relationship connecting orbital periods with planetary distances. Planets farther from the Sun take longer to complete their journeys. The mathematical pattern links the entire known planetary family. This is more than improving a table. For the first time, the separate motions of planets begin looking like parts of one coherent system. Still, Kepler does not possess the modern concept of gravity. He searches for a physical cause and suspects that the Sun somehow influences planetary motion. His ideas combine mathematics, physical intuition, and concepts that later science will discard. Scientific progress is rarely a clean staircase. A person can discover a profound law while misunderstanding why that law works. Kepler also carries intellectual habits that now seem wonderfully strange. He searched for mathematical harmonies within the planetary system, and once attempted to connect planetary spacing with the 5 regular geometric solids. Imagine nesting perfect shapes between planetary spheres. It was beautiful. It was also wrong. Kepler's willingness to abandon that cherished construction when observations resisted, it reveals something important about his work. The sky was allowed to disagree. Scholars still debate how best to characterize Kepler's unusual mixture of astronomy, theology, mathematics, astrology, and physical speculation. Modern disciplinary boundaries fit him poorly. For Kepler, patterns in nature could carry mathematical and spiritual significance at the same time. You should resist turning him into a modern scientist wearing 17th-century clothing. He belonged completely to his own age, yet his planetary laws survive. Outside the window, Mars continues moving through its ellipse. It does not know that anyone has discovered the pattern. The planet has followed approximately the same gravitational rules since long before humans existed. That thought carries you backward for a moment. More than 4.5 billion years earlier, The young solar system formed from a rotating cloud of gas and dust. Material gathered around the newborn sun. Dust grains collided and accumulated. Larger bodies emerged through repeated impacts and gravitational attraction. Eventually, planets formed. Earth became one of them. Mars became another. Nothing about that process created perfect philosophical circles. Real planetary systems are shaped by motion, gravity, collisions, resonances, and interactions extending across immense periods. Kepler cannot know this history, but his ellipses begin describing its consequences. The universe is being discovered twice again. First matter formed worlds, billions of years later. One of those worlds produced creatures capable of measuring how the others move. There is something quietly remarkable about that. You stand outside beneath a cold European night. Your breath becomes faintly visible in the air. Damp earth smells stronger after sunset, and distant wood smoke hangs over the landscape. Mars appears as a reddish point. Without a telescope, it remains almost featureless. Yet mathematics now tells you something your eyes cannot directly see. That point is tracing an ellipse. This represents a subtle transformation in human knowledge. Observation no longer means only describing visible appearances. Mathematics can reveal invisible structure behind them. Still, one great question remains. Why? Why should planets follow ellipses? Why should they accelerate near the sun? Why should distant planets require longer periods? Kepler's laws describe the pattern beautifully, but they do not provide the complete physical mechanism. The answer will eventually connect planetary motion with something as ordinary as a falling object. Before that connection can be made, another transformation arrives. It begins with glass. Lenses have existed in various forms for centuries. Spectacles had already helped aging eyes focus on nearby objects. Then, around the beginning of the 17th century, instrument makers in the Netherlands produced devices combining lenses to magnify distant scenes. The precise history of the telescope's invention is complicated. Several individuals appear in early records, and historians continue examining competing claims concerning who first constructed or conceived particular designs. What matters for astronomy is what happens next. News of the instrument travels. In 1609, Galileo Galilei hears descriptions of the device and begins constructing improved versions. You can imagine the first experience. A tube rests against your hands. The material feels cool. You raise it toward a distant building, adjust the focus, and suddenly details leap closer. The effect seems almost magical. Then someone points the instrument upward. That simple movement changes humanity's relationship with the universe. For all previous astronomical history, the naked human eye has been the primary detector. Large instruments improved angular measurement. Mathematics improved prediction. Writing extended memory. But the eye itself still received essentially the same amount of celestial detail available to prehistoric observers. Now the eye acquires assistance. The moon becomes a landscape. Galileo sees irregularities suggesting mountains and depressions rather than a perfectly smooth celestial sphere. Sunspots later provide further evidence that heavenly bodies are not flawless and unchanging. The Milky Way dissolves into enormous numbers of faint stars. Then Galileo turns his telescope toward Jupiter. In January 1610, he notices small points of light near the planet. Their positions change from night to night. He continues watching. Soon, the implication becomes difficult to avoid. These objects are orbiting Jupiter. You can imagine the quiet shock. Not everything circles Earth. There, visible through a tube of glass, is a small planetary system with its own center of motion. The observation does not by itself prove that Earth circles the Sun, but it damages the idea that every celestial object must revolve directly around Earth. Venus provides even stronger evidence. Through the telescope, Venus displays a sequence of phases. Its changing illuminated appearance is incompatible with the traditional Ptolemaic arrangement in its classical form. A sun-centered or Tychonic arrangement explains the observations much better. The old cosmos is losing observational ground. Galileo's telescopic claims also provoke disagreement. Early telescopes produce imperfect images. Some observers struggle to reproduce what others report. Could strange spots come from the instrument itself? Could lenses distort celestial objects? Such skepticism is not inherently foolish. A new instrument must establish trust. Every technology that reveals something previously invisible creates this problem. You must learn whether you are seeing nature or the flaws of your equipment. Slowly, telescopic observation proves its value. Saturn appears strangely shaped through early instruments, although its rings will not be correctly understood until later. The Moon possesses texture. Jupiter has companions. Venus changes phase. The Sun carries blemishes. The heavens have become physical places. You lower the telescope. For a moment, everything looks ordinary again. Crickets sound beyond the building. Your fingers feel the rough surface of the tube, while the smell of oil and cool night air surrounds you. Above, Jupiter appears once more as a simple bright point, but you cannot truly see it that way anymore. Knowledge has changed the light. The universe is no longer merely a set of wandering lamps attached to mathematical paths. It contains worlds. Those worlds move according to patterns Kepler has begun to describe. And somewhere between a planet sweeping around the sun and an apple falling toward the ground lies a single physical principle humanity has not yet fully recognized. The telescope has changed what you can see. Soon, gravity will change what all those motions mean. In 1687, Isaac Newton published a work that connected the falling of ordinary objects with the movement of worlds. By then, telescopes had already unsettled the old heavens. You can imagine yourself beneath an English evening sky, where damp grass brushes against your shoes and smoke rises from nearby chimneys. The air carries the smell of wet soil and burning wood. Above you, the moon moves quietly through darkness. For generations, that moon had belonged to the celestial realm. A falling stone belonged to Earth. Newton helped reveal that both could obey the same physics. The distinction sounds obvious now. It was not obvious then. Aristotelian traditions had treated earthly and celestial motions differently. Kepler had described planetary paths mathematically, while Galileo had investigated motion closer to the ground. Newton brings these threads together. His great work presents laws of motion and universal gravitation within a mathematical framework capable of explaining both falling bodies and planetary orbits. The word universal matters. Every mass attracts every other mass. Earth pulls on the moon. The moon pulls on Earth. The sun attracts the planets, while the planets also attract the sun and one another. You are participating in this gravitational conversation at this very moment. Earth pulls you downward. You pull Earth upward. Your effect is simply too tiny to notice. That is one of gravity's charming humiliations. You are cosmically involved, but not especially influential. Newton's famous falling apple story has become almost impossible to separate from his public image. According to later accounts, seeing an apple fall encouraged him to think about gravity extending toward the moon. Whether one dramatic apple produced the decisive insight is doubtful. Scientific discoveries usually develop through prolonged work rather than picturesque moments beneath convenient fruit trees. Still, the story preserves a profound question. Why should gravity stop at the treetops? Suppose it does not. Suppose Earth's gravitational influence extends far into space. The moon can then be understood as continually falling toward Earth while moving sideways quickly enough to keep missing it. An orbit is a fall that never reaches the ground. You picture throwing a stone horizontally. It travels forward and downward before striking Earth. Throw it faster and it travels farther. In an idealized thought experiment, enough horizontal speed allows the falling object to curve around Earth instead of colliding with it. The moon is doing something related on an enormous scale. Kepler's ellipses now acquire a physical explanation. The sun's gravity continually bends planetary motion. Planets closer to the sun experience stronger gravitational effects, while their speeds and distances combine to produce the orbital patterns Kepler measured. Two intellectual worlds become one. The physics of the ground reaches the heavens, yet Newtonian gravity contains its own mystery. How can bodies separated by empty space influence one another? Newton provides an extraordinarily successful mathematical description without offering the final underlying mechanism. Later generations will wrestle with that question. More than 2 centuries afterward, Einstein will replace the picture with something deeper. For now, Newton's theory works astonishingly well. Astronomers can use it to predict motions throughout the solar system. Small deviations become meaningful. If a planet fails to follow its expected path, perhaps an unseen object's gravity is disturbing it. That possibility will eventually lead to remarkable discoveries. Meanwhile, telescopes continue improving. Early refracting telescopes suffer from optical problems, including colored fringes around bright objects. Longer instruments can reduce some difficulties, producing telescopes of almost comical proportions. Some become extraordinarily unwieldy. Astronomers are learning a recurring lesson. Better views of the universe often require increasingly inconvenient equipment. Newton himself develops a practical reflecting telescope, using a curved mirror rather than relying entirely on a large objective lens. Reflecting designs will eventually dominate many major observatories. The reason is physical. Mirrors can gather and focus light without producing the same kind of chromatic aberration found in simple lenses. More light means access to fainter objects. That principle becomes central to observational astronomy. Your eye is limited. A telescope is fundamentally a light collector. The larger its aperture, the more photons it can gather from distant sources. Imagine standing beside an early telescope during a cold night. Metal chills your fingertips. The wooden structure creaks slightly as the instrument moves. Your eye presses toward the eyepiece while a companion adjusts the alignment. Then Saturn comes into focus. By the middle of the 17th century, Christian Huygens had interpreted Saturn's strange appearance as a ring surrounding the planet. He also discovered Titan, Saturn's largest moon. The solar system is becoming populated. Galileo's 4 bright moons of Jupiter are joined by further satellite discoveries. The planets are no longer solitary wandering lights. They possess systems of their own. Comets also begin losing some of their ancient mystery. Edmund Halley applies Newtonian ideas to cometary observations and recognizes that comets seen in different years could represent the same returning object. He predicts the return of a particular comet. It appears again in 1758 after Halley's death. The comet later bears his name. Prediction has become a powerful demonstration of theory. A celestial visitor, once treated as unpredictable, can now be placed within gravitational astronomy. There is something calming about this transformation. The universe has not become less beautiful. It has become more connected. A comet, a moon, a falling stone, and Earth itself participate in the same gravitational order. Yet this success creates another question. How large is the system containing all these stars? For ancient observers, stars could be imagined upon a distant celestial sphere. Telescopes reveal more of them, but they do not immediately reveal their distances. A star remains a point. Even powerful magnification does not turn ordinary stars into visible disks because they are enormously far away. The old problem of stellar parallax remains. If Earth truly moves around the Sun, nearby stars should shift slightly during the year. Astronomers keep looking. Their instruments are still not quite precise enough. The absence of measurable parallax pushes the stars farther away in human imagination. The universe expands without anyone physically traveling through it. Meanwhile, another idea grows stronger. Perhaps the Sun is itself a star. If so, the stars may be distant suns. That possibility has circulated in various forms for centuries, but telescopic astronomy makes it increasingly difficult to regard the stars as mere decorations surrounding the planetary system. The cosmos begins to acquire depth. Scholars still disagree about how early modern thinkers interpreted the nature and distribution of stars. Cosmological speculation often reached beyond what observations could firmly establish. That gap between evidence and imagination remains familiar today. The best science must know where measurement ends. By the 18th century, astronomers are cataloguing ever more celestial objects. Some faint patches remain stubbornly unresolved. They are called nebulae, meaning cloudy objects. What are they? Perhaps some are nearby clouds. Perhaps others are enormous star systems. The telescope reveals the mystery before it explains it. You step away from the eyepiece. The night has grown colder. A thin layer of moisture covers the grass, and the smell of extinguished lamp oil drifts from the observing area. Overhead, the Milky Way crosses the sky. To your naked eyes, it remains a pale, luminous band. Through telescopes, countless stars appear within it. Humanity now understands the motions of planets with unprecedented power. But the wider universe remains almost completely unknown. How many stars belong to the Milky Way? What shape does their system form? Does the Milky Way contain nearly everything? Or are other vast collections hidden among those faint nebulae? A new generation of telescope builders will begin asking these questions. One of them will construct enormous instruments and spend night after night counting stars. His name is William Herschel, and with him, humanity will begin trying to map the architecture of the stellar universe itself. In 1781, William Herschel was examining the night sky when he noticed an object that did not behave like an ordinary star. You can imagine standing nearby in the cold English darkness. Moisture gathers on the grass, and the smell of damp earth mixes with smoke from distant chimneys. Herschel's telescope points upward while the wooden structure creaks softly as it moves. The unusual object appears slightly different from neighboring stars. At first, Herschel suspects a comet. Continued observations reveal something far more remarkable. It is a planet. The world, eventually named Uranus, becomes the first planet discovered with a telescope, expanding the known boundaries of the solar system beyond Saturn. For thousands of years, humanity had known the same naked-eye planets. Now technology has added another. The universe has not changed. Human vision has. Herschel becomes one of the great observational astronomers of the 18th century, assisted extensively by his sister Caroline Herschel. Caroline makes important astronomical contributions herself, including discoveries of comets and work on catalogues. Their nights require patience. You can picture Caroline recording observations while William remains at the telescope, calling out what he sees. Ink darkens the paper. Cold air creeps through clothing. The telescope gathers light that naked eyes cannot collect efficiently enough on their own. William constructs increasingly ambitious reflecting telescopes. His famous large instrument possesses a mirror roughly 48 inches across. The telescope is enormous for its age. It also creates practical difficulties. Large scientific instruments have always possessed a talent for turning simple observing sessions into engineering projects. Yet the purpose is clear. More aperture gathers more light. More light reveals fainter objects. Herschel wants to understand the stellar system surrounding the Sun. The Milky Way has been visible since prehistoric humans first looked upward, but its physical structure remains uncertain. Galileo had shown that its glow contains countless stars. Now Herschel attempts something audacious. He tries to map it. His method involves counting stars in different directions. If stars are distributed somewhat uniformly, then directions containing more visible stars might correspond to greater depths through the stellar system. You can imagine sweeping the telescope slowly across the heavens. One field contains dozens of stars, another contains far more. Numbers accumulate. From these counts, Herschel constructs a rough picture of the Milky Way as a flattened stellar system, with the Sun located somewhere within it. The map is deeply imperfect. Interstellar dust hides enormous portions of the galaxy, making distant stars invisible at optical wavelengths. Herschel does not know how severely this affects his counts. Still, the attempt represents a major conceptual change. The stars are no longer merely points on a celestial surface. They form a structure. Humanity is beginning to ask where the sun sits inside that structure. Herschel also observes nebulae. Some resolve into clusters of stars under stronger telescopes. Others remain cloudy. This encourages a major question. Could every nebula eventually resolve into stars with sufficient magnification? Or are some genuinely diffuse material? Astronomers will argue over such possibilities for generations. The debate becomes intertwined with an even larger question about whether certain nebulae might be separate stellar systems comparable to the Milky Way. Evidence remains insufficient. The universe is teasing observers again. Better instruments reveal enough to create a question before revealing enough to settle it. Meanwhile, another discovery changes astronomy without requiring a larger telescope. Light itself becomes the subject. In 1800, William Herschel experiments with sunlight, separated into colors by a prism. He measures temperatures beyond the visible red portion of the spectrum and detects heating where his eyes see no light. Today, you call this infrared radiation. Invisible information has entered astronomy. A year later, Johann Wilhelm Ritter investigates radiation beyond the violet end and discovers effects associated with what becomes known as ultraviolet radiation. Human eyesight occupies only a narrow slice of nature's available electromagnetic information. The implication will eventually be enormous. The universe is sending messages your eyes cannot see. Another crucial clue had appeared earlier. When sunlight passes through a prism, it spreads into a rainbow of colors. In the early 19th century, Joseph von Fraunhofer carefully studies the solar spectrum and maps numerous dark lines crossing it. These lines look like missing pieces of color. At first, their deeper meaning is uncertain. Later laboratory work by scientists, including Gustav Kirchhoff and Robert Bunsen, helps establish that chemical elements produce characteristic spectral patterns. Suddenly, starlight becomes a chemical message. This is one of astronomy's most astonishing transitions. You cannot visit the sun. You cannot scoop material from an ordinary star into a bottle. Yet you can determine what elements exist there by examining light. Imagine sitting in a darkened 19th century room. A narrow beam enters the instrument. Glass separates the light into colors, and delicate lines appear across the spectrum. The room smells faintly of metal, dust, lamp oil, and heated equipment. You lean closer. Those lines have crossed astronomical distances. They carry information about matter. Astronomy begins becoming astrophysics. The question is no longer only where celestial objects move. Now you can ask what they are. Spectroscopy reveals that stars contain familiar chemical elements. The heavens are not made from some entirely separate celestial substance. The same kinds of matter found on Earth appear throughout the cosmos. Helium provides a particularly delightful example. During observations of the sun's spectrum in the 19th century, a spectral signature is identified that does not match known terrestrial elements. The element is named helium in connection with the sun. Only later is helium found naturally on Earth. For once, humanity discovers an element in the sky before recognizing it beneath its feet. The stars are becoming laboratories. Photography transforms astronomy as well. Human eyes are excellent but temporary detectors. A photographic plate can collect faint light over extended exposures and preserve the result. Now the sky can leave its own physical record. An observer does not need to sketch every detail. Light does some of the recording. Long exposures reveal stars too faint for unaided vision. Photographs can be compared across years. Objects that move, brighten, fade, or change position become easier to identify. Precision increases again. The same historical rhythm repeats. A new instrument changes what questions can be asked. Then, in 1838, Friedrich Bessel achieves something astronomers have sought for centuries. He measures stellar parallax convincingly for the star 61 Cygni. Earth's orbital motion finally reveals itself directly through the tiny apparent shift of a nearby star. The effect is minuscule. That small angle carries an enormous message. The stars are tremendously distant. The ancient objection to a moving Earth had finally been answered by measurement. Earth really does travel around the Sun. The stars were simply too far away for earlier observers to detect the change in viewpoint. Distance itself had hidden the evidence. During the 19th century, astronomers also learned that stars differ in temperature, spectra, luminosity, and physical character. Some stars appear redder, others appear blue or white. Spectral classification gradually organizes these differences. Understanding what they mean takes time. Historians of astronomy still examine how changing theories, laboratory physics, observational techniques, and institutional practices shaped these classification systems. The categories did not arrive fully understood. Sometimes science organizes first and explains later. Another planet also enters the solar system through mathematics. Astronomers notice that Uranus does not move exactly as expected. Perhaps an unseen planet is gravitationally disturbing it. Calculations predict where that world might be found. In 1846, Neptune is observed near the predicted region. Newtonian gravity has effectively pointed a telescope toward an invisible planet. It is a spectacular success, yet the larger mystery remains unresolved. Beyond the solar system, telescopes reveal spiral nebulae. Some possess graceful swirling forms. What are they? One possibility is that they are structures within the Milky Way. Another is breathtaking. Perhaps they are independent island universes, immense stellar systems separated from our own by unimaginable distances. You step outside an observatory near the end of the century. The air is cold and still. A photographic plate has been exposed somewhere behind you, silently gathering ancient photons. Above, the Milky Way looks much as it always has. But you now know that stars are distant suns containing familiar elements. You know their light can reveal temperature and chemistry. You know Earth moves because stellar parallax has finally been measured. The universe has become physical. It has become measurable across distances once considered impossible. Yet humanity still does not know whether the Milky Way is the universe or merely one structure inside something vastly larger. The answer is waiting inside those faint spiral clouds, and when it arrives, even the enormous stellar universe of Herschel will suddenly become only one galaxy among countless others. In 1919, a British expedition carried delicate astronomical equipment to the island of Principe off the western coast of Africa. The goal was to photograph stars during a total solar eclipse. You can imagine the humid air pressing against your skin as clouds drift overhead. Tropical vegetation smells wet and heavy after rain, while insects hum around unfamiliar trees. The sun slowly disappears. Daylight weakens. Then darkness arrives. For several extraordinary minutes, stars become visible close to the blackened sun. Their apparent positions might help test a radically new description of gravity. The theory belongs to Albert Einstein. 4 years earlier, in 1915, Einstein had completed the general theory of relativity. Newton had described gravity with extraordinary success for more than 2 centuries. His mathematics predicted planetary motions, tides, comets, and countless other phenomena. Yet Newton's framework was not the final layer. Einstein approaches gravity differently. Space and time are not separate backgrounds where cosmic events merely happen. They belong to a combined structure called space-time. Matter and energy influence its geometry. Objects then follow paths through that curved geometry. You can picture a planet orbiting the sun. Newton describes an attractive gravitational interaction between the bodies. Einstein describes the sun altering space-time around itself, while Earth follows the geometry produced there. The deeper mathematics is far more subtle than the familiar stretch sheet analogy often used to illustrate it. Still, the central idea is astonishing. Gravity becomes geometry. Even light must respond. If starlight passes close to the sun, its path should bend slightly. The eclipse of 1919 creates an opportunity to measure that effect because the sun's overwhelming brightness is temporarily hidden. Arthur Eddington participates prominently in the observational effort. Photographs taken during the eclipse are later compared with reference star positions. The results are announced as supporting Einstein's prediction. Newspapers transform Einstein into an international celebrity. The universe has acquired curved spacetime. The historical story, however, is more complicated than the famous headline. Researchers have examined the uncertainties, observational limitations, plate quality, and analysis surrounding the 1919 measurements. Later observations confirm gravitational light bending with much greater precision. The early eclipse results were important, but scientific confirmation did not rest permanently upon one dramatic expedition. Again, evidence accumulates. The cosmos rarely changes its entire description in a single afternoon. Relativity also transforms ideas about time. Clocks do not necessarily tick at identical rates everywhere. Motion matters. Gravity matters. Time itself participates in the physical universe. These effects are tiny in ordinary life. Modern technologies eventually become precise enough that they cannot ignore them. Yet while physicists reconsider space and time, astronomers are confronting an enormous geographical question. Where exactly is the Milky Way? And are those spiral nebulae inside it? By the early 20th century, astronomers disagree strongly about the scale of the stellar system and the nature of spirals. The disagreement becomes famous through a 1920 event, later called the Great Debate. Harlow Shapley argues for a very large Milky Way. He has studied globular star clusters and used their distribution to infer that the Sun is not near the galaxy's center. This is another quiet demotion. Earth had lost the center of the planetary system. Now the Sun loses a privileged central position within the Milky Way. Heber Curtis takes different positions concerning the size of the Milky Way and argues that spiral nebulae are separate stellar systems. Neither side possesses every correct piece. That is often how important debates work. Nature does not arrange evidence into convenient teams. The decisive measurements require reliable distances. Distance is one of astronomy's persistent difficulties. You cannot stretch a measuring tape between galaxies. Instead, astronomers build a ladder of methods. Nearby stars can be measured through parallax. More distant objects require other indicators. One of the most important comes from Henrietta Swan Leavitt, working with photographic plates. Leavitt studies variable stars called Cepheids. These stars brighten and fade periodically. She discovers a relationship between the period of variation and intrinsic brightness for Cepheids she studied in the Magellanic Clouds. The longer the period, the greater the luminosity tends to be. This provides astronomy with a powerful distance tool. If you know how bright an object truly is and compare that with how faint it appears, you can estimate its distance. Leavitt has given astronomers a way to extend their ruler much farther into space. Her work emerges from a broader community of women who analyzed astronomical photographic plates at Harvard College Observatory. Their painstaking classifications and measurements become fundamental to modern stellar astronomy. The work can seem quiet. Glass plates are examined. Numbers are recorded. Patterns slowly appear. Yet the scale of the universe is hiding inside those repetitive tasks. During the 1920s, Edwin Hubble uses the Large Hooker Telescope at Mount Wilson Observatory in California to study the Andromeda spiral. Imagine climbing into the observing environment on a cold mountain night. Metal feels icy beneath your hand. The dome smells faintly of machinery, dust, and oil. Outside, the darkness above Los Angeles is far deeper than it will become in later decades. The telescope points toward Andromeda. Hubble identifies variable stars there, including Cepheids. Their inferred distances place Andromeda far beyond the dimensions of the Milky Way, as then understood. The implication is enormous. Andromeda is not a small cloud inside our galaxy. It is another galaxy. Those spiral nebulae scattered across photographs can be vast stellar systems in their own right. The universe suddenly fills with galaxies. Imagine the psychological scale of that change. For prehistoric observers, the visible stars seemed to define the heavens. For Herschel, they formed an enormous stellar system. Now that system becomes one galaxy among many. Andromeda alone contains an immense population of stars. Its light takes roughly 2.5 million years to reach Earth. When you look at it, you see ancient light. The photons entering your eye began traveling long before modern humans built cities. Even this discovery is only the beginning. Astronomers photograph more galaxies. They appear in nearly every direction. Some are spirals, some are elliptical, others have irregular forms. The universe possesses structure on scales that earlier generations had no observational means to imagine. Then another pattern emerges. Astronomers examine the spectra of galaxies and notice shifts in their spectral lines. Many distant galaxies show redshifts. Their light arrives stretched toward longer wavelengths. Earlier work by Vesto-Slipher had already measured substantial radial velocities for spiral nebulae. Those observations become crucial to the developing picture. Hubble and others later compare galaxy distances with recession measurements. A broad relationship appears. More distant galaxies generally recede faster. Georges Lemaitre had already connected general relativity with an expanding universe and derived a relationship between distance and recession. The historical credit is therefore richer than the simplified story of one astronomer discovering expansion alone. Observation and theory converge through several people. The universe is expanding. This does not mean galaxies are simply exploding outward through pre-existing empty space from one central location. On sufficiently large scales, space itself participates in the expansion. There is no ordinary central point within the observable expansion from which every galaxy flies. From another distant galaxy, the large-scale pattern would also show other remote galaxies receding. You sit quietly beneath the Mount Wilson sky. The telescope above you gathers photons that have crossed millions of years. The air smells of pine and cold stone. Far below, scattered lights mark human settlements. For thousands of years, people asked how the lights in the sky moved. Now humanity has discovered something stranger. The entire large-scale universe has a history. If galaxies are farther apart today than they were yesterday, then in the distant past, they must have been closer together. Run the cosmic expansion backward. Distances shrink. Matter becomes denser. Temperatures rise. The question that once concerned the arrangement of planets has expanded beyond recognition. Astronomy is now approaching the history of space-time itself, and somewhere deep in that history lies a universe so hot and dense that stars, galaxies, planets, and even ordinary atoms cannot yet exist. In 1927, Georges Lemaitre published a solution to Einstein's equations describing a universe that could expand. You can imagine the intellectual strangeness of that suggestion. For most of human history, the cosmos had been treated as a grand arrangement of objects whose positions and motions needed explanation. Now the arrangement itself could change. Space was no longer merely the stage. The stage could expand. You stand beneath a European night sky during the late 1920s. A tram rattles somewhere beyond the darkened street, while coal smoke hangs faintly in the cool air. Above you, the stars look perfectly still. Nothing appears to be expanding. That is because the effect becomes obvious only across enormous distances. Your body does not expand with the universe. Neither does Earth. The solar system remains gravitationally bound, as does the Milky Way. Even many neighboring galaxies belong to systems where local gravity overwhelms cosmic expansion. Expansion reveals itself between sufficiently distant structures. To understand the evidence, you return to spectroscopy. A galaxy's light contains spectral lines produced by particular atoms. When those lines appear, shifted toward longer wavelengths. Astronomers describe the effect as redshift. Several physical mechanisms can create redshift. For distant galaxies within cosmology, the dominant interpretation involves the expansion of space stretching the wavelength of traveling light. Imagine a photon beginning its journey from a remote galaxy. It crosses space for millions or billions of years. During that journey, the universe expands. By the time the photon reaches your telescope, its wavelength has been stretched along with the changing cosmic scale. The light carries a record of expansion. Vesto Slipher had measured substantial spectral shifts of spiral nebulae before their extragalactic nature was firmly established. Those measurements later became crucial. Then distance estimates became available. During the late 1920s, a relationship between distance and recession emerged from theoretical and observational work. The farther away a galaxy lies, broadly speaking, the greater its cosmological redshift tends to be. Today, this relationship is associated with both Hubble and Lemaitre. The naming itself reflects a larger historical lesson. Scientific discoveries are often collaborative processes, later compressed into convenient labels. The universe cares little about whose surname survives. Einstein initially resisted a changing cosmos. When he had applied general relativity to cosmology, he introduced a term called the cosmological constant into his equations. This helped permit a static cosmic model. A static universe seemed natural. After all, why should the cosmos as a whole expand or contract? But a perfectly static universe under gravity presents difficulties. Once observations increasingly support expansion, the cosmological constant appears unnecessary for maintaining the old picture. A famous story claims Einstein later called its introduction his greatest blunder. Historians remain uncertain about the exact wording and circumstances. The quotation became much more famous than its documentation. There is a pleasing twist. Decades later, the cosmological constant returns to cosmology in connection with accelerated expansion. Perhaps the alleged greatest blunder was merely early. During the 1930s, the expanding universe creates a profound question. If you run expansion backward, mathematically, matter becomes increasingly compressed. Could the universe have begun in an extremely dense state? Lemaitre develops an early version of such an idea. Other scientists explore related possibilities. Not everyone is convinced. A universe with a beginning carries scientific, philosophical, and sometimes theological implications that make discussions especially lively. But cosmology must ultimately answer to observation. Alternative models emerge. One influential competitor is the steady-state model, developed later by Fred Hoyle, Hermann Bondi, and Thomas Gold. In this picture, the universe expands, but maintains roughly the same large-scale appearance through continuous creation of matter. There is no uniquely hot beginning. The cosmos remains eternal in its broad statistical character. This model has appealing simplicity. It also makes predictions that can be tested. The term Big Bang itself enters popular scientific language through Hoyle, who uses it during a radio broadcast while discussing the competing cosmological picture. Whether he intended it mockingly is less certain than popular retellings sometimes suggest. Either way, the nickname stays. It is slightly misleading. The Big Bang was not an explosion occurring at one location inside empty space. There is no ordinary blast center you could travel toward. Instead, the early universe describes a state in which space everywhere was much hotter and denser than it is now. Every sufficiently distant region was closer to every other region. You cannot stand outside it. There is no known external viewing platform. The universe is the event. This distinction is difficult because human intuition evolved for campfires, falling stones, weather, predators, and journeys across landscapes. It did not evolve for relativistic spacetime. Cosmology asks ordinary brains to imagine extraordinary geometry. So you return to evidence. If the early universe was hot and dense, traces of that condition should remain. One important prediction concerns the abundance of light elements. During the earliest minutes, temperatures were high enough for nuclear reactions to occur throughout the cosmos. Protons and neutrons combined into nuclei. Most ordinary matter eventually remained hydrogen. a substantial fraction became helium. Small quantities of other light nuclei also formed. The predicted proportions depend upon conditions in the early universe. Observations broadly support this primordial nucleosynthesis picture, but an even more dramatic prediction concerns ancient light. In a sufficiently hot young universe, matter exists as an ionized plasma. Electrons cannot remain attached to nuclei for long. Photons repeatedly scatter from charged particles, making the universe opaque. Imagine trying to see through dense, glowing fog. Light cannot travel freely for great distances. As expansion continues, the universe cools. Eventually, roughly 380,000 years after the beginning of the hot expansion, temperatures become low enough for electrons to combine with nuclei into neutral atoms. Photons can then travel much more freely. The cosmic fog clears. That ancient radiation should still exist today. Expansion would have stretched its wavelengths enormously, cooling its apparent temperature until the radiation occupied the microwave region. During the 1940s, researchers including George Gamow, Ralph Alpher, and Robert Herman developed important theoretical work concerning the hot early universe and its radiation. The predicted relic remains undetected for years. Then, in the 1960s, two radio astronomers encounter a stubborn noise. Arno Penzias and Robert Wilson are working with a sensitive antenna in New Jersey. Their equipment detects microwave radiation that seems to come from every direction. You can imagine standing beside the large horn-shaped antenna. Summer air feels heavy against your skin. Electronic equipment hums nearby. The instrument keeps hearing a faint background signal. They investigate possible sources of contamination. The antenna itself receives attention. Even pigeons become part of the story because they have left what scientific descriptions politely call dielectric material inside the equipment. Cleaning does not remove the signal. The noise remains. Nearby, another group of researchers at Princeton has been preparing to search for precisely the kind of cosmic background radiation predicted by hot universe models. The connection is soon recognized. In 1965, the discovery is published. The universe has left behind a thermal afterglow. Today, this radiation is called the cosmic microwave background. Its temperature is only about 2.7 degrees above absolute zero. It fills the observable universe. When sensitive instruments map it, they reveal tiny variations in temperature across the sky. Those variations are extremely small, yet they represent something enormous. They are associated with early differences in density that gravity later amplifies into cosmic structure. Galaxies will grow from these faint irregularities. Galaxy clusters will emerge. Stars will ignite. Planets will eventually form. And on at least one planet, radio astronomers will build an antenna capable of detecting the ancient light. You stand beneath the night sky again. Nothing looks different. The Milky Way remains a pale band overhead. Cool air touches your face, while distant traffic murmurs beyond the darkness. Yet invisible microwave photons are passing through the scene. They have traveled for more than 13 billion years. Humanity once watched planets without knowing they were worlds. Now instruments detect light released before any star existed. The expanding universe is no longer merely a mathematical possibility. Its history has begun leaving multiple independent fingerprints. And if you continue following those fingerprints backward, you approach an era where even atoms disappear. Matter becomes an incandescent plasma, and the familiar universe dissolves into conditions increasingly remote from ordinary experience. 13.8 billion years ago, the observable universe existed in conditions hotter and denser than anything you encounter naturally today. You cannot stand nearby and watch. There is no nearby. There is no known external darkness surrounding a fireball, and no empty room into which the universe suddenly explodes. Space itself is part of the story. You have reached the limit where familiar images become unreliable, so you follow the evidence carefully. Begin around 380,000 years after the hot expansion began. The universe is already enormous. but far denser than today. Its temperature has fallen enough for electrons to remain bound to atomic nuclei. Hydrogen becomes abundant neutral matter. Helium is already present. Photons that had repeatedly scattered through the earlier plasma can finally travel much greater distances without constant interruption. The cosmos becomes transparent. Those photons are still arriving. You cannot see them with your eyes because cosmic expansion has stretched their wavelengths into the microwave region. Modern instruments can detect them from every direction. This is the cosmic microwave background, encountered by Penzias and Wilson. Its existence provides a remarkable observational bridge into deep time. You are not merely calculating the early universe. You are receiving its light. Now move backward. The temperature rises. Atoms cannot remain intact. Electrons separate from nuclei, leaving a hot plasma of charged particles and radiation. Go farther backward, and conditions become hotter still. Within the first several minutes, nuclear reactions occur rapidly. Protons and neutrons combine. The expanding universe cools too quickly to manufacture large amounts of heavy elements, so hydrogen and helium dominate the resulting ordinary matter. Small amounts of deuterium, helium-3, and lithium also emerge. This period is called Big Bang nucleosynthesis. Its predictions can be compared with astronomical measurements. That comparison is one reason the hot early universe is taken seriously. The theory does not survive because its story sounds dramatic. It survives because different observations agree with consequences of the same underlying picture. Continue backward into the first seconds. Temperatures become extraordinary. Matter exists in forms impossible to maintain in your bedroom, on a mountaintop, or almost anywhere else in the present universe. Particles collide relentlessly. Neutrinos interact with the primordial environment before largely decoupling from ordinary matter. Quarks and gluons participate in conditions unlike the stable protons and neutrons familiar today. The sensory imagination begins failing here. There is no cool surface beneath your feet. There is no ordinary smell, because molecules capable of producing smells do not exist. There is no gentle breeze. There is only an intensely energetic physical state expanding and cooling. That absence of familiar sensation is itself worth noticing. Human language developed in a universe already old and cold. Words like fire, cloud, explosion, and fog are borrowed from everyday experience. They help. They also mislead. Now approach the earliest fractions of a second. Modern physics becomes less certain. Cosmologists can extrapolate known theories backward, but eventually the energies become so extreme that general relativity and quantum physics must somehow be reconciled. A complete experimentally confirmed theory of quantum gravity does not yet exist. This means the phrase "the beginning" requires care. The Big Bang model describes the evolution of the universe from an early hot, dense state with extraordinary success. It does not provide a confirmed description of an absolute creation from literal nothing. That distinction is frequently lost. You may ask what happened before the Big Bang. The most scientifically responsible answer is wonderfully unsatisfying. We do not know. Some models propose earlier phases. Others suggest bouncing cosmologies, quantum origins, or broader structures in which our observable universe represents only one region. Certain ideas involve multiple universes. None currently possesses the observational status of the standard hot Big Bang framework. Cosmologists still debate which, if any, descriptions can meaningfully extend time beyond the earliest regimes accessible to established physics. Even the word "before" may become complicated if time itself behaves differently near the earliest boundary. This is uncertainty in its proper form, not ignorance disguised as certainty. One influential idea concerning the extremely early universe is cosmic inflation. Inflation proposes a brief period of extraordinarily rapid expansion. It was developed partly to address puzzles within standard cosmology, including why widely separated regions of the universe appear so similar. Consider the cosmic microwave background. Regions now separated by enormous distances possess nearly identical temperatures, without some mechanism connecting their earlier histories. That uniformity seems surprising. Inflation provides a possible explanation. Before rapid expansion separated them enormously, regions could have shared conditions more closely. Then a very brief expansion magnified tiny scales into cosmic ones. Quantum fluctuations could also have been stretched during this process. Those small irregularities may become the seeds from which later structures grow. Galaxies owe their existence to imperfection. A perfectly uniform universe would be rather dull. Matter would have little reason to gather preferentially in one place rather than another. Instead, tiny density differences allow gravity to begin its patient work. Over millions and billions of years, slightly denser regions attract additional matter. The differences grow. Eventually, stars and galaxies emerge. Modern measurements of the cosmic microwave background reveal minute temperature variations consistent with a remarkably structured early universe. Satellites have transformed these measurements. COBE provided crucial evidence that the background has an almost perfect thermal spectrum and detected large-scale anisotropies. UMAP later mapped fluctuations with much greater precision. The Planck mission improved measurements further. Humanity has effectively photographed the universe in infancy. The image looks like a mottled field rather than a baby photograph, which is probably for the best. From those patterns, cosmologists infer information about cosmic age, geometry, composition, and the formation of structure. The universe appears to be approximately 13.8 billion years old. Ordinary matter represents only a modest portion of its total energy budget. Dark matter contributes much more. Dark energy appears to dominate the present cosmic energy density. Most of the universe is therefore composed of things whose fundamental nature remains mysterious. This is a curious destination for centuries of scientific progress. Humanity measures the cosmos more precisely than ever and discovers how much remains unexplained. Now let time move forward again. The universe expands. It cools. Nuclei survive. Atoms eventually form. The cosmic microwave background begins its long journey. Then darkness settles across the universe. There are no stars yet, no planets, no galaxies glowing as they do today. Hydrogen and helium fill expanding space, while gravity slowly amplifies the small density variations inherited from earlier conditions. Astronomers sometimes call this interval the cosmic dark ages. It lasts for tens of millions of years before the first stars ignite. Imagine darkness on a scale no human night has ever approached. There is gas. There is gravity. There is invisible dark matter influencing structure. But there are no stellar lamps. Then matter begins collecting within growing gravitational wells. Gas becomes denser. Compression raises temperatures. The first stellar objects approach ignition. Exactly when and how the earliest stars formed remains an active field of research because direct observations of this era are exceptionally difficult. Modern telescopes are beginning to probe remarkably early galaxies, forcing astronomers to refine models of how quickly cosmic structure developed. The first stars were probably unlike many stars surrounding the Sun today. They formed almost entirely from primordial hydrogen and helium, because heavier elements had not yet been manufactured in significant quantities. Those heavier elements require stars. Carbon does not arrive ready-made in large cosmic abundance. Neither does oxygen, silicon, calcium, and iron must emerge through later stellar processes and explosive events. The universe must learn chemistry through stars. You wait in imagination within that ancient darkness. There is still no smell, no ground, and no air against your skin. Only hydrogen gathers silently under gravity. Millions of years pass. Density increases. A stellar core becomes hotter. Eventually, nuclear fusion begins. For the first time, after the long cosmic darkness, a star shines. Then others follow. Their ultraviolet radiation begins changing the surrounding gas. The universe slowly becomes luminous again. Those first stars are temporary. Some will die dramatically and scatter newly forged elements into space. Later generations of stars will form from enriched material. Around some of them, disks of dust will become planets. One such star will appear more than 9 billion years after the hot beginning. Around it, a small rocky world will form. And on that world, atoms forged through cosmic history will eventually arrange themselves into living observers who look upward and ask where everything came from. Long after the first stars appeared, the universe began manufacturing the ingredients from which worlds and eventually living bodies could be assembled. You can imagine one of those early stars forming inside a collapsing cloud of primordial gas. There is no landscape beneath it. No wind touches your face, and no scent exists in the surrounding darkness. Hydrogen and helium gather silently while gravity compresses the cloud toward its center. Then the core becomes hot enough for fusion. A star switches on. The phrase sounds almost casual. The process changes the universe. Inside stellar cores, light atomic nuclei combine under tremendous pressure and temperature. Hydrogen fusion produces helium while releasing energy that can support a star against gravitational collapse. For millions or billions of years, depending upon its mass, a star can remain balanced between two tendencies. Gravity pulls inward. Pressure associated with the hot interior pushes outward. You see only the light escaping from the surface. But deep inside, nuclear reactions gradually transform matter. More massive stars can proceed through additional stages. Helium contributes to the production of carbon and oxygen. Later burning stages in sufficiently massive stars create progressively heavier nuclei. The details are complicated. Different elements arise through different stellar and explosive processes, and not every familiar element comes from precisely the same source. That complexity matters. The poetic phrase that humans are made of stardust is broadly meaningful, but the actual chemical ancestry is richer than one kind of dying star. Some elements are produced inside ordinary stars. Others are created or dispersed during stellar explosions. Still others, including many very heavy nuclei, can be generated through environments involving rapid neutron capture. Neutron star mergers are now known to be important contributors to this cosmic chemistry. The gold in a ring may therefore carry an astonishing ancestry, long before it passed through a mine, workshop, shop window, or human hand. Its atoms may have been forged during an extraordinarily violent astrophysical event. Cosmic history hides inside ordinary objects. Early stars begin enriching their surroundings when they lose material or die. Gas that once contained almost nothing beyond hydrogen and helium acquires carbon, oxygen, silicon, iron, and other heavier elements. Later stars form from this enriched material. Each generation inherits chemistry from earlier generations. The universe develops memory through matter. You move forward across billions of years. Galaxies grow through gravitational attraction, collisions, mergers, and continued star formation. The Milky Way itself develops through a long and complicated history rather than appearing suddenly in its modern form. Smaller systems merge into larger structures. Streams of ancient stars preserve traces of past encounters. Its central regions evolve. A rotating disk becomes prominent. Dark matter surrounds the visible galaxy within a much larger gravitational halo. Exactly how the earliest phases of the Milky Way unfolded remains an active research subject. Astronomers reconstruct its past, using stellar ages, chemical compositions, motions, simulations, and observations of distant galaxies. Galactic archaeology is an appropriate name. Stars become fossils. Roughly 4.6 billion years ago, one cloud of enriched gas and dust within the Milky Way begins collapsing. Perhaps nearby stellar activity contributes to the conditions. The exact trigger remains uncertain. Gravity does most of the lasting work. As the cloud contracts, rotation causes material to flatten into a disk. At the center, most of the mass gathers into the young sun. Around it, dust circulates. Imagine floating above that disk, although there would be no safe place for you there. Gas streams through the young system. Dust grains collide. Tiny particles stick together through various processes. They become larger aggregates. Those aggregates contribute to planetesimals, bodies large enough for gravity and collisions to shape their continuing growth. The early solar system is not peaceful. Objects collide repeatedly. Some merge, some fragment, some are thrown into different orbits, others are expelled entirely. Planet formation is less like assembling furniture and more like allowing gravity several million years of enthusiastic demolition. Closer to the young sun, heat favors rocky materials. Farther outward, colder conditions permit greater quantities of volatile substances to participate in planetary formation. Eventually, the familiar architecture emerges. Mercury, Venus, Earth, and Mars occupy the inner region. The giant planets dominate farther out. Countless smaller objects remain. Earth forms about 4.54 billion years ago. Its earliest history is violent. Material differentiates inside the young planet. Dense, iron-rich matter sinks toward the interior, while lighter materials contribute to the mantle and crust. A major collision with a planetary body early in Earth's history probably contributes to the Moon's formation. The precise details of this giant impact process remain debated. Different simulations can reproduce various aspects of the Earth-Moon system, but important questions remain concerning composition, timing, and impact geometry. The Moon nevertheless becomes a crucial companion. Its surface preserves a battered record of ancient impacts that Earth's active geology has largely erased. You can touch a terrestrial rock and feel only the present surface. The Moon keeps older scars. As Earth cools, its atmosphere and oceans evolve. Volcanic gases contribute to the atmosphere. Water comes from multiple sources, including material incorporated during Earth's formation and later contributions from water-bearing bodies. The simple image of all Earth's oceans arriving aboard comets is probably too neat. Nature usually refuses the neat version. By more than 3.5 billion years ago, life clearly existed on Earth, and evidence may point toward even earlier origins. How non-living chemistry first became self-sustaining biology remains one of science's greatest unresolved questions. Researchers investigate possibilities involving hydrothermal environments, shallow waters, mineral surfaces, organic molecules, and other settings. No complete pathway has been established. That uncertainty does not diminish the achievement of understanding life's later evolution. It marks an unfinished boundary. Somewhere on the young Earth, chemistry crossed a threshold. Matter began copying information. Variation appeared. Natural selection gained something upon which to act. From there, biological evolution unfolded across immense spans of time. For most of Earth's history, life remained microscopic. There were no forests beneath the stars. No animals looked upward. Microorganisms transformed the planet quietly. Photosynthetic organisms eventually released increasing quantities of oxygen, profoundly altering Earth's atmosphere and chemistry. To many earlier organisms, oxygen was not a pleasant gift. It was chemically disruptive. One species' useful waste product can become another species' planetary crisis. Complex cells eventually appeared. Multicellular organisms diversified. Marine ecosystems became elaborate. Plants spread across land. Animals followed. Continents shifted while species evolved and vanished. Mass extinctions repeatedly changed the direction of biological history. The dinosaurs dominated terrestrial ecosystems for an immense interval. Then, about 66 million years ago, a large asteroid struck near what is now the Yucatan Peninsula. The impact contributed to a global environmental catastrophe and a mass extinction. Non-avian dinosaurs disappeared. Mammals survived and diversified into many newly available ecological roles. Eventually, one branch produced primates. Much later came hominins. The timeline becomes almost uncomfortable now. The universe is roughly 13.8 billion years old. Earth is more than 4.5 billion years old. Our own species, Homo sapiens, has existed for only a tiny fraction of that duration. Recorded history occupies a thinner slice still. All the astronomers you have met appear near the final instant of the cosmic story. Babylonian observers, Aristarchus, Ptolemy, medieval astronomers, Copernicus, Kepler, Galileo, Newton, Herschel, Einstein. They are almost simultaneous when measured against cosmic time. Yet those brief human lives uncover events extending billions of years into the past. The discovery becomes possible because the universe preserves evidence. Rocks preserve radioactive clocks. Fossils preserve biological history. Starlight preserves information about distant matter. The cosmic microwave background preserves an image of the young cosmos. Atoms themselves preserve clues to stellar ancestry. You now sit beneath a modern night sky. Perhaps cool grass touches your hands. You smell soil and leaves while distant traffic hums beyond the darkness. Above you, familiar stars shine between patches of thin cloud. Your body belongs completely to this story. Hydrogen inside you traces its ancestry toward the early universe. Carbon depends upon stellar nucleosynthesis. Calcium in your bones required earlier generations of stars. Iron in your blood belongs to a cosmos capable of manufacturing heavy nuclei. You are not observing the universe from outside. The observer is assembled from the thing being observed. That realization would have been inaccessible to the earliest people watching lunar phases beside their fires. They nevertheless began the chain. They looked. Later generations recorded. Others measured. Others built instruments. And now those instruments can detect planets orbiting other stars, collisions of black holes, invisible matter through its gravity, and cosmic expansion accelerating across unimaginable distances. The universe has produced observers. Those observers have finally become capable of examining regions far beyond their own galaxy. And what they find there is stranger than the luminous universe alone can explain. In 2015, two enormous detectors in the United States registered a vibration smaller than the width of a proton. Nothing shook beneath your feet. No sound crossed the landscape. Yet an event from the distant universe had finally reached Earth after traveling through space for more than 1 billion years. Two black holes had collided. You can imagine standing near one of the observatories on an otherwise ordinary day. Dry air moves across the ground. Machinery hums quietly, and warm metal carries the faint smell of dust. Inside, lasers measure distances with extraordinary precision. For most of human history, astronomy depended almost entirely upon light. Now humanity can detect ripples in space-time itself. Einstein's general relativity had predicted gravitational waves a century earlier. Accelerating masses can disturb space-time, sending waves outward at the speed of light. Usually, these waves are incredibly weak by the time they reach Earth. The merging black holes were different. Each contained many times the mass of the Sun. As they spiraled together, their orbital motion accelerated until the two horizons joined. The final object settled into a larger black hole. A portion of the system's mass became energy carried away by gravitational waves. The detectors known as LIGO measured their passing. Humanity had gained another sense. The progression is remarkable. Your distant ancestors used naked eyes. Later observers used geometrical instruments. Galileo added the telescope. Photography allowed light to accumulate. Spectroscopy revealed chemistry. Radio astronomy opened invisible wavelengths. Space observatories escaped atmospheric limitations. Now gravitational waves reveal events that may produce little ordinary light. The universe has always been speaking through many channels. Humans gradually learned how to listen. Black holes provide one of the strangest subjects in that conversation. They emerge naturally from general relativity when enough mass becomes concentrated within a sufficiently small region. A boundary called the event horizon forms. Beyond it, escape to the outside universe becomes impossible according to classical relativity. Even light cannot return. That does not mean black holes are cosmic vacuum cleaners roaming through space and swallowing everything nearby from a safe distance. Their gravity behaves according to their mass. If the Sun could somehow be replaced by a black hole with exactly the same mass, Earth's orbit would remain approximately unchanged. The sunlight problem would be rather more serious. Black holes can form when massive stars collapse. Much larger black holes occupy the centers of many galaxies. The Milky Way contains one called Sagittarius, a star, with a mass of roughly 4 million suns. In 2022, the Event Horizon Telescope collaboration released an image revealing the glowing environment surrounding this object. A few years earlier, the same global network had produced the famous image of the black hole in galaxy M87. These are not photographs of black holes as illuminated solid objects. The dark central region is associated with the black hole's shadow against surrounding emission. Again, instruments convert invisible or difficult information into something human senses can understand. Radio telescopes distributed across Earth effectively cooperate as an enormous virtual telescope. The planet itself becomes part of the instrument. Black holes also expose the unfinished boundary between relativity and quantum physics. Stephen Hawking's work showed that quantum effects allow black holes to possess thermal radiation. Over unimaginable timescales, an isolated black hole can therefore lose mass. The result creates profound questions about information and quantum mechanics. Physicists continue debating how a complete theory should describe these objects. The darkest things in the universe remain intellectually bright. Yet black holes are not the largest mystery. Look at a galaxy. Its stars orbit the galactic center. When astronomers measure those motions, visible matter alone often cannot provide enough gravity to explain what they observe. Evidence from galaxy clusters points in the same direction. So does gravitational lensing. Something unseen appears to contribute substantial mass. This unknown component is called dark matter. The name is refreshingly straightforward. We know it behaves gravitationally. We do not know its fundamental identity. Ordinary atoms appear to account for only a minority of the matter in the cosmos. Dark matter does not seem to emit, absorb, or reflect ordinary light in the familiar way. You therefore detect it mainly through what its gravity does. Imagine seeing footprints in snow while the walker remains invisible. You cannot describe the person from footprints alone. But pretending nobody walked there becomes increasingly difficult. One famous piece of evidence comes from the bullet cluster, where observations of hot, ordinary matter and gravitationally inferred mass show different spatial distributions after a cluster collision. Such systems strengthen the case that unseen mass behaves differently from ordinary luminous material. Exactly what dark matter consists of remains unknown. Candidates have included several hypothetical particles and other possibilities. Experiments continue searching. The mystery is genuine. Then the universe becomes stranger again. During the late 20th century, astronomers studied distant exploding stars called Type Ia supernovae. These events can serve as standardized distance indicators after appropriate calibration. Researchers expect cosmic expansion to be slowing because gravity attracts matter. The observations reveal something surprising. Expansion appears to be accelerating. Two major teams announce evidence for this result in 1998. Something is driving the large-scale universe toward faster expansion. Cosmologists call the unknown cause dark energy. The name describes our ignorance almost as clearly as dark matter does. A cosmological constant within Einstein's equations can reproduce the observed acceleration. Whether dark energy is simply this constant or reflects deeper physics remains uncertain. Together, dark matter and dark energy dominate the standard cosmological accounting. Everything familiar to you belongs to the minority. Stars, planets, oceans, trees, human bodies, books, telescopes, and coffee are made from ordinary matter. Cosmically speaking, ordinary matter is not the main ingredient. the universe has developed a sense of humor. While cosmologists investigate invisible components, astronomers are also discovering worlds. In 1995, astronomers announced the detection of a planet orbiting the Sun-like star 51 Pegasi. It was not the first confirmed exoplanet of any kind, since planets had already been found around a pulsar. But 51 Pegasi b helped transform the search around ordinary stars. It was surprising. The planet is a gas giant, orbiting extremely close to its star. Our solar system had encouraged expectations based on its own architecture. Other planetary systems immediately began refusing to cooperate. Thousands of exoplanets have since been confirmed. Some orbit extremely close to their stars. Others travel on unusual elongated paths. Some systems contain several compactly arranged worlds. There are planets larger than Earth, but smaller than Neptune, a category absent from our own solar system. Nature had conducted planetary experiments long before humans started theorizing about them. Modern astronomers detect these worlds using several methods. A planet may cause its star to wobble gravitationally. It may pass across the stellar face and produce a tiny decrease in brightness. Some planets can be imaged directly under favorable circumstances. Atmospheres can sometimes be studied through spectroscopy. Once again, light becomes chemistry. The technique developed from 19th-century laboratory physics now reaches across interstellar space toward alien skies. This naturally raises an ancient question in modern form. Are you alone? No confirmed evidence currently demonstrates extraterrestrial life, yet the ingredients associated with life as humans understand it are widespread. Carbon exists throughout the cosmos. Water occurs in many environments. Organic molecules form naturally. Planets are common. Whether biology itself is common remains unknown. Scientists search for potentially habitable environments on Mars, icy moons, and distant exoplanets. Radio surveys also listen for possible technological signals. The silence so far can be interpreted in many ways. Perhaps life is rare. Perhaps simple life is common, while technological civilizations are unusual. Perhaps distances and timescales make communication unlikely. Perhaps our searches have barely begun. Researchers disagree because the evidence remains painfully limited. You can look across an ocean after examining one cup of water, but you should be cautious about announcing what lives everywhere beneath the waves. Modern astronomy therefore combines extraordinary precision with enormous uncertainty. You know the universe is expanding. You can measure the cosmic microwave background. You can detect black hole mergers. You can identify atmospheres around some distant worlds. Yet you cannot explain most cosmic matter at the particle level. You do not know what drives accelerated expansion fundamentally. You do not know whether life exists elsewhere. This is not scientific failure. It is the frontier created by earlier success. Every solved mystery reveals a larger landscape behind it. You step outside after the instruments have finished collecting another night's data. The air feels cooler now. A faint breeze carries the smell of vegetation and distant rain. Above you, stars appear almost motionless against the darkness. Some possess planets. Some will eventually collapse. Far beyond them, galaxies are separating as cosmic expansion continues. Invisible dark matter helps shape their structure. Dark energy influences the future of the largest scales. Gravitational waves pass through Earth without disturbing your sleep. Humanity has come astonishingly far from that first prehistoric fire. Yet one final direction remains. You have followed the universe backward toward its earliest measurable conditions. Now you can turn around. You can allow time to move forward beyond humanity, beyond Earth, beyond the Sun, and eventually beyond almost every shining star. The universe has a past. It also has a future. About 5 billion years from now, the Sun will approach the end of its long, stable adulthood. You can imagine looking toward it from an impossible place of safety, far beyond the familiar Earth of today. The sunlight would still feel recognizable at first, yet the star has been changing slowly throughout its life. even while appearing dependable across every human generation. Stars are temporary. That realization completes one of astronomy's longest intellectual journeys. The ancient sky seemed permanent. Constellations returned season after season. The sun rose reliably. The Milky Way crossed the darkness with an appearance older than memory. Modern astronomy reveals something different. Almost everything you see is evolving. The sun formed roughly 4.6 billion years ago from collapsing gas and dust. It currently spends most of its life fusing hydrogen into helium within its core. That fuel will not last forever, as hydrogen becomes depleted in the central region. The sun's internal structure will change. Its outer layers will eventually expand dramatically. The sun will become a red giant. Long before this transformation reaches its greatest extent, increasing solar brightness will make Earth's surface progressively less hospitable. Oceans will not remain unchanged forever. Continents will not survive indefinitely. The atmosphere itself will evolve under increasingly intense solar conditions. Exactly how the distant Earth responds depends upon complicated interactions between solar evolution, atmospheric processes, geology, and orbital dynamics. Scientists can model broad outcomes more confidently than every detail. The familiar blue planet has an expiration date. During the red giant phase, the sun will become vastly larger than it is today. Mercury and Venus are expected to face destruction. Earth's precise fate during the sun's maximum expansion involves subtleties concerning solar mass loss and tidal interactions. Researchers continue examining whether our planet would be engulfed. Either way, Earth will have ceased being remotely comfortable long before then. There is something almost amusing about humanity worrying whether the planet gets physically swallowed after its oceans have already disappeared. Cosmology is generous with perspective. Eventually, the sun will shed much of its outer material. The expanding gas will briefly create a beautiful glowing structure around the exposed stellar core. What remains will become a white dwarf. This object will contain a substantial fraction of the sun's former mass, compressed into something approximately comparable with Earth in size. Nuclear fusion will no longer sustain it as before. The white dwarf will simply cool. Slowly, very slowly. The sun's story is ordinary by stellar standards. More massive stars face more violent endings. Some undergo core collapse and explode as supernovae. Their remnants can become neutron stars or black holes. Others lose material through winds before reaching their final states. Lower mass stars can survive far longer than the sun. Small red dwarfs consume their fuel so gradually that none has yet had time to reach the natural end of its main sequence lifetime. The universe is not old enough. That is a wonderfully strange thought. Astronomers can study stars whose eventual deaths lie farther into the future than the entire age of the universe so far. Now you allow billions of years to pass. The night sky changes completely. Constellations dissolve because stars possess their own motions through the galaxy. The familiar patterns were always temporary. The Milky Way and Andromeda are moving toward one another. In several billion years, they are expected to interact and eventually merge into a larger galactic system. The word collision sounds catastrophic. For individual stars, the experience is usually less dramatic. Galaxies contain enormous amounts of empty space between their stars. Direct stellar collisions are therefore unlikely during such a merger. Gravitational interactions, however, can reshape stellar orbits and disturb gas dramatically. New patterns emerge. The night sky from any surviving planetary system could become spectacular. Great arcs of stars might stretch across the heavens, but there may be nobody here to watch. You continue forward. Cosmic expansion proceeds. On the largest scales, distant galaxies move farther away because the expansion is accelerating. Sufficiently remote galaxies will eventually become inaccessible to observers within our gravitationally bound region. Their light becomes increasingly redshifted. Over immense timescales, many galaxies disappear beyond our observable reach. Future astronomers, if any exist, may inherit a lonelier-looking cosmos. This creates an extraordinary historical reversal. Ancient humans lacked instruments, and therefore saw only a tiny portion of the universe. Extremely distant future observers may possess magnificent instruments, but inhabit an era when much of the wider cosmos can no longer send them usable signals. Evidence itself can disappear. Our cosmic era is therefore special in a practical sense. We can still observe the cosmic microwave background. We can still see enormous numbers of external galaxies. We can measure expansion and reconstruct early cosmic history. Far in the future, some of these clues become vastly harder to detect. Knowledge depends partly upon when you exist. Now billions become trillions of years. Star formation gradually declines as galaxies consume or lose usable gas. Long-lived red dwarfs continue shining after stars like the Sun have vanished. Eventually, even they exhaust their fuel. The universe grows darker. Stellar remnants become increasingly dominant. White dwarfs remain. Neutron stars remain. Black holes remain. Cold planets and smaller bodies drift through fading systems. Gravitational encounters can gradually rearrange or eject objects from galaxies. The bright stellar age ends. Cosmologists sometimes call the later period the degenerate era, referring to the kinds of compact objects that remain rather than to any moral decline in the universe. The cosmos has no opinion about terminology. White dwarfs continue cooling toward hypothetical black dwarfs. No black dwarf should exist today because the universe has not existed long enough for one to form. Their existence belongs entirely to theory about the distant future. The timescales now become almost impossible to imagine. You could compare them with human history, but human history becomes effectively invisible beside them. Even Earth's entire geological lifetime becomes a brief opening note. There are uncertainties here. One concerns proton decay. Some theories beyond the standard model predict that protons may eventually decay, but no such decay has been observed. Experiments have established extremely long lower limits for proton stability. If protons decay, ordinary matter will slowly disappear over enormous timescales. If they do not, some remnants can persist much longer. The distant future therefore branches, according to physics, that humanity has not yet resolved. Black holes offer another clock. According to Hawking's theoretical work, black holes are not perfectly eternal. Quantum effects allow them to emit thermal radiation. For ordinary astrophysical black holes, this process is fantastically slow. A stellar mass black hole requires vastly longer than the current age of the universe to evaporate. Supermassive black holes survive longer still, for ages beyond ordinary comprehension. They can remain among the universe's final major reservoirs of concentrated energy. Then they too fade. As a black hole loses mass, its evaporation eventually accelerates. At last, the object disappears into radiation according to the semi-classical picture. Precisely how quantum information behaves throughout this process remains a profound theoretical problem. The universe reaches territory where present physics cannot answer every question confidently. Still, one broad future appears particularly consistent with current observations. If accelerated expansion continues indefinitely and dark energy behaves much like a cosmological constant, the universe approaches a condition often called heat death. The name sounds dramatic. The reality is quieter. Matter and energy become increasingly dilute. Useful differences in energy become harder to exploit. Stars are gone. Black holes eventually disappear. Photons stretch toward longer wavelengths as expansion continues. Events become increasingly rare. The universe does not necessarily end at one dramatic moment. It fades. Other possibilities have been proposed. If dark energy changes with time, different futures could emerge. Some hypothetical models allow expansion to become so extreme that bound structures are eventually torn apart in a big rip. Other cosmological scenarios have considered future contraction or transitions into new states. Current evidence does not establish these alternatives as the expected outcome. The nature of dark energy remains the central uncertainty. You have encountered this pattern before. At every stage of human cosmic discovery, knowledge ends at an edge. Babylonian observers could predict without understanding gravity. Ptolemy could calculate planetary positions while placing Earth incorrectly. Kepler found the shape of orbits without possessing Newton's explanation. Newton described gravity without Einstein's space-time. Einstein transformed gravity while leaving quantum gravity unresolved. Modern cosmologists measure accelerated expansion without knowing fundamentally what dark energy is. The frontier keeps moving. Perhaps future observations will change this picture again. New gravitational wave observatories may reveal events from earlier cosmic epochs. Larger telescopes may study atmospheres around smaller exoplanets. Measurements of dark matter may finally identify its microscopic nature. Experiments may uncover physics beyond current particle theories. A future theory may connect gravity and quantum mechanics successfully. Or nature may surprise humanity with something nobody has thought to search for. That possibility has historical precedent. Nobody watching Mars with naked eyes could have predicted radio astronomy. Nobody examining Ptolemy's tables could have imagined gravitational waves. Nobody peering through Galileo's telescope could have anticipated photographs of the cosmic microwave background. The instruments change, then the universe changes with them. Not physically, conceptually. You return, finally, to the human scale. The journey began beside a prehistoric fire. You watched people notice repeating stars without knowing what stars were. Then clay tablets remembered celestial movements. Geometry turned the sky into a mathematical problem. Astronomers built models around Earth. Later scholars preserved those models, tested them, and improved their measurements. Copernicus moved Earth. Tycho measured. Kepler broke the circle. Galileo extended the eye. Newton connected heaven with the falling stone. Herschel expanded the stellar landscape. Spectroscopy discovered chemistry in light. Einstein curved space-time. Leavitt helped extend the cosmic distance scale. Hubble and others revealed a universe of galaxies. Radio instruments detected the afterglow of the early cosmos. Modern observatories found black holes, exoplanets, dark matter, accelerated expansion, and gravitational waves. The universe was discovered twice. First, matter itself followed a cosmic history. Expansion cooled the young cosmos. Atoms formed. Gravity gathered gas. Stars ignited. Elements accumulated. Galaxies evolved. Planets formed. Life appeared on at least one small world. Then part of that living matter became curious. Atoms began examining atoms. Stardust started measuring stars. For a brief moment in cosmic history, the universe became capable of asking questions about itself. And now the night becomes quiet again. You can imagine lying beneath the same broad darkness that surrounded the earliest skywatchers. Cool air rests gently against your skin, while distant sounds soften and slowly disappear. Above you, ancient light continues arriving. You do not need to follow it any farther tonight. The stars can keep their patient courses without your attention, just as they did before humanity learned their names. Galaxies will turn slowly. Space will continue expanding. The universe has waited billions of years, and it can wait until morning. For now, there is only darkness, distance, and the quiet rhythm of a cosmos still unfolding. You can simply rest beneath it.